40 light-years away from Earth. Scientists discovered something that changed everything we knew about planets. What appeared to be just another rocky world orbiting a distant star turned out to be a place completely different from anything we have ever seen. 55 Cancri E, as it was called, is a planet twice as large as Earth, but with 8 times more mass. Studies showed that at least 1/3 of this entire world may be made of pure, crystalline, shining diamond. Here on Earth, a small diamond is worth a fortune, but there exists an entire planet made of it. The temperature on the surface reaches 2,700 degrees, hot enough to melt metal. This made scientists ask something shocking. If diamonds can form entire planets in other places in the universe, what else precious and rare could be waiting for us in the stars? Prepare to fall asleep while you listen to this video and embark on this fascinating journey. Subscribe to the channel, leave your like and comment from which part of the world you are watching. Get comfortable and relax. Let's begin. Imagine a world where a year passes in less than a day, and the very ground beneath your feet might be made of diamond. That is the mind-bending reality of 55 Cancri E, a planet whose discovery shattered our understanding of what planets could be. This story begins not with a telescope pointed directly at it, but with astronomers studying its parent star, a sun-like star called 55 Cancri A. They were using a clever technique called the radial velocity method, which involves watching for a subtle wobble in the star's motion. This wobble is caused by the gravitational tug of orbiting planets, like a spinning weightlifter slightly swaying as they swing dumbbells around. For years, data from 55 Cancri A indicated a complex system with 4 planets, but something did not add up. The star's wobble had a persistent, tiny rhythm that could not be explained by the 4 known worlds. It was a gravitational signature hinting at a 5th, much closer and more massive planet. The confirmation came in 2004, revealing a planet so close to its star that it completes an entire orbit in just about 18 hours. That is an incredibly short year. A blur compared to our 365-day journey around the Sun. But the real shock came when scientists calculated its density. They had its mass from the radial velocity measurements and its size from later transit observations. Where it passes in front of its star, the density was immense, far too high for a gas giant like Jupiter. Yet its characteristics did not match any ordinary rocky planet like Earth. This discrepancy was the first major clue that 55 Cancri E was something entirely new, a world that refused to fit into our neat categories. It forced astronomers to confront the idea that planets could be made of materials we had never considered possible on such a scale. The discovery meant that our solar system was not the template for all planetary systems. The universe was far more diverse and creative. It opened up a new frontier in cosmic investigation, pushing scientists to develop new models and theories. The radial velocity method had been refined over decades, and this discovery was a testament to its power, showing that patience and precision could reveal hidden worlds. The initial data required sophisticated analysis to separate the signal of this new planet from the noise and the influences of its sibling planets. Think of it like listening to a complex symphony and trying to pick out the sound of a single, very quiet instrument playing a rapid, unique rhythm. That instrument was 55 Cancri A. Its detection was not just about finding another planet. It was about realizing that planetary systems could be packed with worlds in tight orbits, something our own solar system does not prepare us for. The significance extended beyond just adding one more exoplanet to the catalogue. It challenged the very definition of a planet. What do you call a world that is twice Earth's size but 8 times more massive, with a density suggesting something other than rock and iron? This puzzle sparked intense debate and curiosity. The high density pointed towards an interior rich in heavy elements, and given the star's known composition, which is high in carbon, the hypothesis of a carbon-rich world began to take shape. This meant that instead of being made mostly of silicates and iron like Earth, 55 Cancri A could be dominated by carbon, possibly in the form of diamond under extreme pressure. The discovery thus became a gateway to thinking about exotic planetary compositions. It also highlighted the importance of stellar chemistry in planet formation. Stars with higher metallicity, meaning more elements heavier than hydrogen and helium, can give birth to planets with very different building blocks. For 55 Cancri E, the star's carbon-rich environment likely led to a planet where carbon compounds were abundant. The detection method itself was a triumph of collaboration and technology, using instruments like the HIRES spectrograph on the Keck telescope to measure the star's radial velocity with incredible accuracy. The wobble they detected was minuscule, a shift in the star's light spectrum equivalent to a walking pace. But it was enough to reveal a giant world whipping around its star at breathtaking speed. The orbital distance is incredibly small, about 25 times closer than Mercury is to our Sun. This proximity means the planet is blasted with intense radiation and heat. But the density mystery was the key that unlocked its true nature. The discovery of 55 Cancri E also had practical implications for the future of exoplanet science. It showed that small, rocky worlds could exist in extreme environments, and it paved the way for more detailed studies using other methods like the transit technique. When astronomers observed the planet transiting its star, they could measure its radius precisely, which, combined with the mass, gave them that critical density. This combined approach is now standard for characterizing exoplanets. The planet's discovery meant that astronomers had to expand their imagination. No longer could they assume that all terrestrial planets would be similar to Earth or Venus. Here was a world that was arguably more exotic than any science fiction. A super-Earth with a composition that might include vast layers of diamond. This realization was humbling and exciting, reminding us that the universe is full of surprises. It also underscored the value of persistent observation. The data for 55 Cancri E was not obvious at first. It required re-examining existing data and collecting new observations to confirm the planet's presence. The team behind the discovery had to rule out other possibilities, such as stellar activity masquerading as a planetary signal. This rigorous process is a hallmark of good science, and it paid off with one of the most fascinating exoplanets known. The short orbital period meant that studies could be conducted relatively quickly, as multiple orbits could be observed in a single week. This allowed for rapid follow-up observations, which helped solidify the planet's properties. The discovery also sparked public imagination, with headlines often calling it the Diamond Planet. Though the scientific reality is more nuanced, what it truly signified was a leap in our ability to detect and analyze worlds light years away. It proved that we could find planets not just in habitable zones but in infernal realms, expanding our understanding of planetary diversity. The radial velocity method, while powerful, has limitations. It is best at finding massive planets close to their stars, and 55 Cancri A was a perfect candidate. Its discovery encouraged the development of new instruments and space telescopes designed to study exoplanets in greater detail. For instance, the Spitzer Space Telescope later observed the planet's thermal emissions, providing clues about its temperature and atmosphere. The legacy of this discovery is that it forced a paradigm shift. Before 55 Cancri E, many assumed that super-Earths would be scaled-up versions of our own planet. Now, we know they can be entirely different, with chemistries and structures that defy simple classification. This has implications for the search for life, as it shows that habitable conditions require a very specific set of circumstances, and planets like 55 Cancri E are utterly hostile. The high density and likely carbon composition mean that water and organic molecules cannot survive on its surface. Instead, the surface might be a global ocean of lava or a solid crust of diamond and graphite. The discovery thus helped define the boundaries of habitability. It also inspired new theoretical work on planet formation, suggesting that migration plays a key role in bringing planets so close to their stars. 55 Cancri A may have formed farther out in the protoplanetary disk, where carbon-rich materials were abundant, and then migrated inward due to gravitational interactions with other planets. This journey would have stripped away any lightweight atmosphere, leaving behind a dense, refractory core. The discovery process itself is a story of international collaboration, with teams from various observatories contributing data. It highlighted the importance of archival data, as old observations were reanalyzed to find the subtle signals of new planets. This approach has become common in exoplanet research, leading to many more discoveries. In summary, the detection of 55 Cancri E was a revolutionary moment because it revealed a type of world we did not know existed, challenging our categories and expanding our cosmic perspective. It showed that the universe is capable of creating planets out of materials we consider precious, but under conditions so extreme that they are beyond human reach. The discovery was not just about finding a planet. It was about opening our minds to the incredible diversity of planetary systems. It meant that we had to rethink everything from planetary formation to the very materials that make up worlds. This single discovery has influenced countless studies and will continue to do so as we explore more exoplanets with advanced telescopes like the James Webb Space Telescope. The journey to find 55 Cancri E was a testament to human curiosity and technological innovation, proving that even the smallest wobble in a distant star can lead to the most profound revelations. But to truly understand this bizarre diamond world, we have to zoom out and look at the entire cosmic neighborhood it calls home. The story of 55 Cancri A is deeply intertwined with the unique star system it orbits, a system that provided the perfect ingredients for such an exotic planet to form. This isn't a single star system like our own. It's a binary system, dot, meaning there are two stars gravitationally bound to each other. The primary star, 55 Cancri A, is the one that hosts our diamond planet and its siblings. It's a yellow dwarf star, often described as a cousin to our Sun because it's very similar in size and mass. But this cousin has a key difference. It's metal-rich. In astronomy, dot, metals doesn't mean iron and steel. It refers to any element heavier than hydrogen and helium. 55 Cancri A has a much higher abundance of these elements, particularly carbon, compared to our Sun. This elevated metallicity is the crucial first piece of the puzzle. It means the protoplanetary disk of gas and dust from which the planets formed was also rich in these heavier elements, creating an environment where carbon-based molecules and minerals were plentiful building blocks. The second star in the system, 55 Cancri B, is a small, dim red dwarf. It orbits the primary star at a much greater distance, about 1,000 times the distance from Earth to the Sun. This vast separation means that 55 Cancri B has little to no direct influence on the inner planets like 55 Cancri E. Its role is more about the system's overall gravitational architecture. The binary nature of the system itself is fascinating. It shows that planets can form and persist in multi-star systems, which are actually quite common in our galaxy. The stability of the inner planetary system around 55 Cancri A despite the distant stellar companion, tells us that planet formation is a robust process. Within this environment, 55 Cancri E is not an only child. It is part of a complex family of at least 5 known planets, labelled B through F, each with its own strange story. This makes the system a fantastic natural laboratory for studying how different types of planets coexist and interact. Before the discovery of E, astronomers had already identified 4 other worlds, all gas giants orbiting farther out. The presence of these giant planets is another critical factor. The innermost of these giants, 55 Cancri b, is a hot Jupiter-like world with an orbit of about 14.6 days. Its gravitational influence, along with the other outer planets, likely played a massive role in the early history of the system. The current theory is that 55 Cancri e did not form in its present scorching location, a mere stone's throw from its star. It probably formed much farther out, in the colder regions of the protoplanetary disk where carbon-rich materials like graphite and methane ice were abundant. As it grew from collisions and accretion, the gravitational pull from the giant planets, especially during the system's chaotic youth, likely sent this protoplanet migrating inward. This grand migration delivered it to its current hellish orbit, where the intense stellar heat then stripped away any primordial atmosphere of hydrogen and helium, leaving behind the dense, refractory core we detect today. So, the system itself acted as a cosmic slingshot, placing this carbon-rich world into the furnace. The other planets in the system provide context for E's extreme nature. Beyond planet B, there is planet C, another gas giant with an orbit of about 44 days, and planet F, a Saturn mass world with an orbit of about 260 days, the outermost known planet. 55 Cancri d is a true behemoth, a giant with a mass about 4 times that of Jupiter, on a wide 14-year orbit. This entire configuration, with multiple massive planets, creates a complex gravitational dance. The interactions between these worlds can subtly tweak each other's orbits over millions of years, a process known as orbital resonance or dynamical friction. This complex dance helped to shape the final architecture of the system, ensuring its long-term stability despite the intense forces at play. The star 55 Cancri A itself is a bit older than our Sun, and its high metallicity is thought to be a key reason why it was able to form such a rich planetary system. Stars with more heavy elements are more likely to have planets, and more likely to have rocky planets with unusual compositions. The specific ratio of carbon to oxygen in a star is particularly important. In our solar system, the ratio favours oxygen, leading to planets like Earth that are built from silicate rocks. But in the 55 Cancri system, the ratio is skewed towards carbon. This means that when planets were condensing from the disk, carbon-based minerals like silicon carbide and graphite were more common than silicate minerals. Under the immense pressures inside a large planet like 55 Cancri A, that graphite can transform into diamond, creating the vast layers we now hypothesize. The distant red dwarf companion, 55 Cancri b, while not directly heating the inner planets, is part of the system's history. Its presence might have influenced the outer reaches of the protoplanetary disk long ago, perhaps helping to truncate it or affecting the formation of the outermost planet. From the perspective of 55 Cancri A, the primary star would dominate the sky, appearing huge and blazingly bright. The distant red dwarf would appear as nothing more than a particularly bright star in the eternal day, if it were visible at all against the glare. The existence of this binary system also helps scientists test models of planet formation in more complex environments than single-star systems like our own. It shows that gravity is the ultimate architect, and planets can find stable orbits even in seemingly crowded stellar neighborhoods. The discovery of multiple planets in this system was a milestone in exoplanet science. It was one of the first systems known to have so many worlds, predating the famous TRAPPIST-1 system. Studying the interactions between these planets allows astronomers to understand migration patterns and system stability. For instance, the orbits of the planets in the 55 Cancri system are not perfectly circular. They have slight eccentricities, which can be clues to past gravitational encounters. The presence of the gas giants also means that the system could potentially harbour smaller, undiscovered planets in more temperate zones. Though none have been confirmed yet, the focus, however, remains on the inner world, because its properties are so extreme. Its location, so close to the star, means it experiences tidal forces that are thousands of times stronger than what the Earth feels from the Moon. These forces have likely locked its rotation, so one side permanently faces the star in a blistering day side and the other faces the cold of space, a somewhat cooler night side. This tidal locking is a direct result of its close orbit within the gravitational grip of its star. The system's architecture, with E so close in and the giants farther out, is a common configuration we see in many exoplanet systems, suggesting that inward migration is a standard part of planetary evolution. The metal-rich nature of 55 Cancri A also has implications for the potential habitability of other worlds in the system, while E itself is a hellscape. The outer planets might have large moons that, in theory, could have conditions for life, though that is pure speculation. The main lesson from studying the 55 Cancri system is that diversity is the rule, not the exception. Our solar system, with its clear division between small, rocky inner planets and large, gaseous outer planets, is just one possible outcome. Here, we have a system with a super-Earth of diamond in the inner region and multiple gas giants further out. This tells us that planetary systems can form in many different ways, depending on the initial conditions of the star and its disk. The high metallicity was the seed that allowed for a carbon-rich world to exist. Without that specific chemical makeup, 55 Cancri E might have been a more conventional, silicate-based super-Earth like those found in other systems. Its very existence is a testament to the variety of materials available in the galaxy for building planets. Understanding this system in detail helps astronomers refine their search for other exotic worlds. By looking at the chemical fingerprint of a star, they can make predictions about the types of planets that might orbit it. A star with a high carbon-to-oxygen ratio becomes a prime candidate in the hunt for more diamond worlds or other carbon-dominated planets. The 55 Cancri system serves as a benchmark, a Rosetta Stone for deciphering the link between stellar chemistry and planetary composition. It's a reminder that every planet is a product of its environment, and to understand the world, you must first understand its sun, and in this case, its suns. The dynamic history of migration and gravitational interactions painted a picture of a system that is both violent and stable, having settled into an arrangement that has lasted for billions of years. This cosmic context transforms 55 Cancri A from a mere curiosity into a logical, if extreme, consequence of its birthplace. It is not a random oddity, but a direct result of the physical and chemical processes at work in its particular corner of the universe. The system continues to be a focus of observation, with telescopes like the James Webb Space Telescope poised to learn even more about the atmospheres and compositions of its planets, starting with the most intriguing one, the diamond world itself. This ongoing study will undoubtedly reveal more secrets about this fascinating stellar family and the extraordinary world that shines at its heart. So, With that cosmic context in mind, let's zero in on the planet itself and unpack what makes it so physically bizarre. 55 Cancri E is classified as a super-Earth, but that term is almost misleading because it implies a larger version of our own world. And this thing is anything but. Its radius is about 2 times that of Earth, which sounds manageable, but its mass is a staggering 8 times greater. That right there is the first clue that we are dealing with something profoundly different. To put it in perspective, period, if you could stand on its surface, which you absolutely could not, the gravity would crush you instantly. It is more than twice what we experience here. The real kicker, the number that made astronomers do a double take, is its density. Density is mass divided by volume, and for 55 Cancri E, it is immense. Earth has a density of about 5.5 grams per cubic centimetre, which is already pretty dense, but this planet's density is nearly twice that. This is not a small difference. It is a fundamental discrepancy that screams that the planet is made of stuff that is much heavier and more compact than the materials we are used to. Think about it this way. If you had a planet made of the same rock and iron as Earth, but 8 times more massive and only twice as wide, the density would be higher, but not this high. The math simply does not add up for a standard terrestrial planet. This was the smoking gun that forced scientists to abandon the idea of a simple rocky world and consider far more exotic compositions. The high density means that a significant portion of the planet must be composed of elements that are very heavy and can be packed tightly together under extreme pressure, in the conditions found deep within a super-Earth. Ordinary silicate rocks, the kind that make up Earth's mantle, would not be dense enough to account for the measurements. This is where the carbon-rich nature of the system comes back into play. Carbon, in its various forms, can achieve much higher densities than silicates, especially when subjected to the insane pressures present in a planet this massive and this close to its star. The initial calculations, based on models of planetary interiors, suggested that up to 1/3 of the planet's mass could be carbon, and under those pressures, carbon crystallizes into diamond. So, we are not talking about a planet with a few diamond veins. We are potentially looking at a world with a layer hundreds or even thousands of kilometers thick made primarily of diamond, possibly surrounding a more traditional core of iron and silicon. This is not just a precious gem. It is a fundamental structural component of the entire world. The sheer scale is mind-boggling. 3 entire Earth masses of diamond is a quantity so vast it bankrupts the imagination and any conceivable notion of value. The physical characteristics do not stop at just density and composition. The planet's proximity to its star means it is tidally locked, with one hemisphere perpetually facing the stellar inferno and the other facing the cold of space. This creates an extreme temperature gradient. But the high density and likely rigid internal structure might influence how heat is distributed across the planet. The dayside temperature is hot enough to melt iron and vaporize rock, so the surface, if it is solid, must be made of something with an extraordinarily high melting point. Graphite and diamond fit that bill perfectly, with diamond having one of the highest melting points of any known material. The intense heat and pressure also mean that the geology is unlike anything we know. There is no water, no plate tectonics as we understand them. Instead, the planet might have a geology of carbon, with possible carbon-based lava flows or even a global ocean of carbon-rich magma. The high gravity would also affect any potential geological activity, making volcanic eruptions, if they occur, far more violent yet constrained by the strength of the diamond-rich crust. Another key physical aspect is the planet's reflectivity, or albedo. A surface covered in diamond or graphite would have a very different way of interacting with light compared to Earth's surface. Diamond is highly transparent, but under the extreme conditions on 55 Cancri E, the surface is likely not pristine crystal, but a tortured, pressurized mass, possibly mixed with other minerals, which could affect how much stellar radiation it absorbs or reflects. Observations of the planet's thermal emissions have helped constrain these models, showing a huge temperature difference between day and night sides, which is consistent with a lack of a substantial atmosphere to redistribute heat. This absence of a buffering atmosphere is another physical characteristic tied directly to its mass and location. The star's radiation and wind have likely stripped away any gaseous envelope it might have once had, leaving the dense core exposed. The planet's orbit itself is a physical characteristic of extreme dynamics. Whipping around its star in just 18 hours, it experiences gravitational forces that are immense, contributing to the internal pressures and the tidal locking. This rapid orbit also means that from our vantage point, we can observe transits and eclipses relatively frequently, which is how we could measure its radius so precisely. The combination of transit data and radial velocity data gave us the mass and radius, and thus the density dot, in a beautiful example of how different observational techniques complement each other. Understanding these physical properties is not just about cataloguing a weird world. It forces us to rewrite the textbooks on planetary science. 55 Cancri E proves that the category of rocky planet is far too broad. We now have to consider carbon planets as a distinct class. Worlds where the dominant chemistry is based on carbon rather than oxygen and silicon. This has huge implications for how we search for and characterize exoplanets around other stars. If we see a star with a high carbon to oxygen ratio, we can now predict that any rocky planets it hosts might be these ultra-dense, diamond-rich worlds, rather than Earth-like ones. The physical characteristics of 55 Cancri A are a direct challenge to our anthropocentric view of planets. We often assume that life requires a planet like Earth, but this world shows that the universe can create planets that are utterly hostile to life as we know it, yet fascinating in their own right. Its size and mass place it in a regime that is actually quite common in our galaxy. Super-Earths are among the most frequently detected exoplanets. But 55 Cancri A tells us that not all super-Earths are created equal. Some might be water worlds, some might be iron planets, and some, like this one, Dot, are diamond worlds. This diversity is what makes exoplanet science so exciting. The extreme density also tells a story about the planet's formation and history. To become so dense, it must have lost a lot of its lighter elements, like hydrogen and helium, which is consistent with the migration model that brought it close to the star where such volatile materials would be boiled away. What remains is the refractory core, the heavy elements that can withstand the heat. In this case, those heavy elements were predominantly carbon and its compounds. The internal structure is modelled as having an iron-rich core, similar to Earth's, but then a thick mantle of diamond, and possibly a crust of graphite. Under the pressures in the mantle, the carbon is stable as diamond, but if geological processes bring material to the surface where pressures are lower, it could transform into graphite. This means the surface might be a complex and dynamic landscape of changing carbon allotropes, though the intense heat likely keeps everything in a state of constant transformation. The planet's moment of inertia, a measure of how mass is distributed inside it, would also be affected by this layered structure, and future precise measurements could help confirm these models. Even the planet's magnetic field, if it has one, Dot, would be influenced by its internal composition and dynamics. A liquid iron core could generate a field, but the presence of a solid diamond mantle might affect convection and thus the strength of any magnetosphere. This is all speculation for now, but it shows how one set of physical measurements, mass, radius, dot, and density, can open up a whole cascade of questions and hypotheses about the inner workings of a world 40 light-years away. In the end, the story of 55 Cancri E's physical characteristics is a story of extremes. Extreme density, extreme temperature, extreme composition. It is a world that pushes the limits of what we thought was possible, and in doing so, it expands our understanding of the cosmos. It is a reminder that nature is often stranger and more wonderful than our imagination, and that the universe holds wonders we are only beginning to glimpse. The study of this planet continues, with new telescopes and instruments promising to reveal even more about its stark and brilliant nature. The stark physical reality of this world naturally leads to the big question: what is it actually made of? How did we move from noticing its bizarre density to the jaw-dropping idea of a planet made of diamond? It was not a wild guess, but a careful scientific process. A detective story piecing together clues from its star and its own behaviour. The initial hypothesis emerged from that critical density measurement combined with the known chemistry of its host star. Remember, 55 Cancri A is metal-rich, with a particularly high ratio of carbon to oxygen. In a planetary system with that kind of chemistry, the building blocks change dramatically. Instead of oxygen bonding with silicon to form silicate rocks, which is what Earth is mostly made of, carbon becomes the dominant player. In such an environment, planets form from carbon-rich materials like graphite and silicon carbide. So, the first part of the theory was straightforward. This planet likely formed from a carbon-rich protoplanetary disk. The next step was to figure out what happens to all that carbon under the immense pressures inside a super-Earth. Scientists ran complex computer models simulating the interior of a planet with 55 Cancri's mass and radius. These models showed that under pressures millions of times greater than Earth's atmosphere, carbon would not remain as graphite. It would undergo a phase transition and crystallize into diamond. The models suggested a plausible internal structure, a relatively small, traditional core of iron and perhaps some silicon, but enveloped by an incredibly thick mantle of diamond, possibly hundreds of miles deep. Above that, there might be a thin crust of graphite. This was the theoretical framework, a world fundamentally engineered from carbon, with diamond as a major structural component, not just a decorative gem. This idea was revolutionary because it proposed a class of planets that simply does not exist in our own solar system. We have rocky worlds and gaseous worlds, but not carbon worlds. The theory provided an elegant explanation for the otherwise inexplicable density. A diamond-rich interior is incredibly dense and rigid, perfectly matching the observational data. But a theory, no matter how elegant, needs observational confirmation. This is where space telescopes entered the picture. The Spitzer Space Telescope played a key role. It observed the planet's thermal emissions, essentially measuring the heat it gives off as it orbits its star. These observations were crucial for several reasons. First, they helped map the temperature difference between the scorching day side and the cooler night side. The huge temperature swing indicated that heat is not being efficiently distributed around the planet, which points to a lack of a substantial atmosphere, a thick atmosphere, especially one with gases like water vapor, would act as a blanket, smoothing out the temperature extremes. The fact that no such smoothing was observed was a major piece of evidence against the planet having a thick, volatile, rich atmosphere. This was important because it ruled out alternative explanations for the planet's properties if it had a massive, dense atmosphere. That could have affected the density calculations or suggested a different composition. Spitzer's data, along with later observations from the Hubble Space Telescope, consistently pointed towards a world with at most a very tenuous atmosphere, perhaps composed of vaporized rock elements like sodium or silicon monoxide, or even no atmosphere at all. This supported the Diamond World hypothesis because it fit the narrative of a refractory planet whose primordial gases had been stripped away by the intense stellar radiation, leaving behind a bare, dense core of carbon and other heavy elements. The confirmation process is ongoing, but the evidence has steadily consolidated around the carbon-dominated scenario. Another line of evidence comes from the absence of certain chemical signatures. If the planet had a significant amount of water or oxygen-based minerals, it might leave a detectable fingerprint in the light passing through any residual atmosphere during a transit. So far, such signatures have not been found, which again steers the conclusion towards a carbon-based chemistry. The scientific method here is beautiful. Propose a model based on fundamental physics and chemistry, then use telescopes to test its predictions. The predictions of the diamond model, a high-density dot, a large day-night temperature contrast, a lack of a substantial water-rich atmosphere, have so far held up to observational scrutiny. It is a great example of how exoplanet science has evolved from simply detecting planets to characterizing their physical and chemical properties in detail. The role of spectroscopy is key here, by analyzing the spectrum of light from the star as the planet transits. Astronomers can theoretically detect which elements are present in the planet's atmosphere. For 55 Cancri E, these studies have been challenging due to the planet's small size and the star's brightness, but they have generally failed to find evidence for molecules like water vapor or oxygen, which you would expect on a silicate world. Instead, the data is consistent with an atmosphere that might contain vapors from a carbon-rich surface. Think of it like this. If the surface is superheated graphite or diamond, the atmosphere could be composed of atoms that have been literally boiled off that surface, like carbon gas or silicon monoxide. This is a far cry from the nitrogen-oxygen atmosphere we breathe. The journey from theory to confirmation also involved ruling out other possibilities. For instance, could the planet be a massive iron ball? While an iron planet would be very dense, it would not fully account for the specific mass-radius relationship and the stellar context. The carbon-rich star makes the carbon planet a much more natural and likely explanation. The computer models were refined to include the specific conditions of extreme heat and pressure, showing that a carbon-dominated interior is not only possible but the most probable scenario given the data. This is not to say the planet is a perfect, flawless diamond sphere. The reality is probably much messier. The interior might be a complex mixture of diamond, other carbon allotropes, and possibly some silicate materials, all churning under tremendous heat and stress. There could be geological activity, like carbon-based volcanism, where lava made of molten carbonates or sulfur erupts onto the surface. The surface itself is likely a nightmare landscape, possibly a global ocean of carbon-rich magma over a substrate of solid diamond. The confirmation of this composition has profound implications. It tells us that the variety of planets in the galaxy is vastly greater than we once imagined. It means that when we look at other stars, especially those with high carbon-to-oxygen ratios, we should be on the lookout for more of these diamond worlds. It forces us to expand our definition of what a rocky planet can be. The tools for this confirmation are getting better all the time. The James Webb Space Telescope, with its incredible sensitivity in the infrared, is the next great step in this detective story. It is capable of performing much more detailed spectroscopy on the light from 55 Cancri A. It might be able to detect the specific chemical signatures of carbon-based molecules in its thin atmosphere, or confirm the absence of water and oxygen once and for all. It could even map the temperature variations across the planet's surface in greater detail, providing clues about the surface composition and heat distribution. Each new observation adds another piece to the puzzle, either strengthening the Diamond World model or forcing scientists to revise it. The process is iterative and self-correcting. What started as a theoretical explanation for a weird density has become a well-supported, though still evolving, model of an entire class of planets. This journey from a wobble in a star's light to a confident statement about a diamond mantle deep inside a distant world is a testament to human curiosity and technological ingenuity. It shows how we can use the laws of physics, applied across light years of space, to understand the nature of worlds we can never visit. The confirmation is not yet 100% absolute. Science rarely deals in such certainties, but the weight of the evidence, from stellar chemistry to internal structure models to thermal emission data, all points overwhelmingly to one conclusion. 55 Cancri E is a carbon world, and a significant part of that carbon is in the form of diamond. It is a confirmed scientific reality that is stranger than the fiction that inspired its nickname. The story of how 55 Cancri A came to be is a cosmic drama of creation and destruction, starting not in the scorching inferno it calls home today, but in the frigid, dark outskirts of the young protoplanetary disk surrounding its star. In those distant, cold regions, far from the heat of 55 Cancri A, temperatures were low enough for volatile, carbon-rich compounds to condense and freeze solid. Molecules like methane, carbon monoxide, and tarry hydrocarbons would have been abundant, coating dust grains in a frosty layer. This was the primordial soup from which the planet would eventually form, an environment rich in the essential building blocks of carbon through countless gentle collisions. These carbon-coated dust particles began to stick together, forming pebbles, then boulders, and eventually planetesimals, the planetary building blocks. This process, known as accretion, is how all planets start. But here, the recipe was special because of the disk's high carbon to oxygen ratio. As these planetesimals orbited, their gravitational pulls began to influence each other, leading to more frequent and violent collisions. Over time, through this chaotic dance of accumulation, a planetary embryo emerged, a core several times the mass of Earth that acted as a gravitational anchor, voraciously pulling in more and more material from its surroundings. This proto-planet was growing in a region where carbonaceous material was the dominant solid, meaning it was accumulating a staggering amount of carbon relative to rock-forming silicates. It was likely on its way to becoming a gas giant, gathering a thick atmosphere of hydrogen and helium from the surrounding nebula. But then, the plot twisted. The gravitational stability of the young system was anything but serene. The other massive planets in the system, particularly the gas giants further out, were exerting their own powerful tugs. These gravitational interactions, over millions of years, can cause a planet's orbit to become unstable. For the young 55 Cancri E, the most likely scenario is that it got caught in a gravitational resonance with one of its larger siblings, a kind of cosmic push and pull that gradually transferred angular momentum and sent the planet spiraling inward. This process, known as planetary migration, is common in young systems and can dramatically alter a world's destiny. So, this carbon-rich core began a long journey from the cold outer disk toward the blazing heat of its star. As it migrated inward, it entered a realm of increasing temperature and radiation. The first thing to go was its primordial atmosphere. The thick envelope of hydrogen and helium that it had accumulated was now being bombarded by intense stellar radiation and powerful winds from the young, active star ... This radiation heated the gases, giving them enough energy to escape the planet's gravity. It was a slow but relentless stripping process, like a cosmic sandblaster, eroding the lightweight atmosphere away until only the dense, refractory core remained. This core was now a naked ball of concentrated carbon and other heavy elements, bereft of its gaseous blanket. But the transformation was not yet complete. As the planet settled into its final, incredibly tight orbit, the internal pressures and temperatures skyrocketed. The pressure from the overlying layers of material, combined with the relentless external heat from the star, created conditions deep within the planet that are unimaginable on Earth. Pressures likely reached millions of times Earth's atmospheric pressure at sea level. Under these extreme conditions, the atomic structure of carbon becomes unstable in its common form of graphite. The carbon atoms are forced into a new, more compact arrangement, the crystalline structure of diamond. This phase change, known as an allotropic transformation, is what ultimately forged the diamond heart of the world. It was not a sudden event, but a gradual process that occurred over eons as the planet's interior equilibrated to its new, hellish environment. The heat from this formation process, from the energy of accretion and the radioactive decay of elements within, would have kept the interior molten for a long time, allowing the diamond to crystallize slowly from a carbon-rich magma ocean. This internal differentiation would have caused heavier elements like iron to sink toward the center, forming a core, while the lighter carbon solidified into a vast mantle of diamond. The surface, meanwhile, was being cooked by the star. Any remaining volatiles or lighter elements were completely boiled away. What was left might have been a global ocean of carbon-rich lava, perhaps composed of molten carbonates or metals, bubbling on top of the solid diamond substrate, the planet's tidal locking, with one side always facing the star, would have further intensified the heating on the day side, potentially creating a permanent lava ocean there, while the night side might have a solid crust of graphite and other carbon allotropes. The entire formation history is a testament to the dynamic and often violent processes that shape planetary systems. It underscores that a planet's final state is not just about where it formed, but also about the journey it undertakes. For 55 Cancri, that journey was a one-way trip from a carbon-rich nursery in the cold depths to a furnace where it was forged into a diamond. This narrative also helps explain why we don't see a similar world in our own solar system. Our system formed from a disk with a lower carbon-to-oxygen ratio, favouring the formation of silicate planets like Earth. The gas giants here, like Jupiter, largely stayed put, preventing any large, inner rocky planets from undergoing such a radical migration. The formation of 55 Cancri is therefore a crucial data point, showing us that planetary systems can evolve along vastly different paths. The gravitational interactions that drove its migration are a key part of the story. The system's other planets, acting like gravitational puppeteers, orchestrated this inward spiral. This migration likely happened early in the system's history, within the first 100 million years or so, while the protoplanetary disk was still present. The gas in the disk can exert a drag on migrating planets, helping to circularize their orbits, which might explain why 55 Cancri orbit is as stable as it is despite its proximity to the star. The stripping of its atmosphere was probably a rapid process in astronomical terms. Once the planet reached the inner system, without the protection of a magnetic field, which a small, solid core might not generate strongly, The stellar wind would have ripped the atmosphere away with relative ease. The internal transformation into diamond, however, would have been a slower, geological process, continuing even today as the planet cools and adjusts. The heat from the star keeps the interior hot, possibly maintaining some level of geological activity, such as convection in the diamond mantle or even carbon-based volcanism. This formation story is not just about the past. It influences the planet's present state and future evolution. The lack of an atmosphere and the diamond composition are direct results of this violent birth and migration. Understanding this helps astronomers predict what to look for in other systems. If we find a star with high metallicity and a known gas giant in a close orbit, we might suspect that there could be a migrated super-Earth like 55 Cancri A lurking even closer in. The discovery of this world has fundamentally changed our understanding of planet formation, showing that migration is a powerful force that can deliver worlds into extreme environments where they are transformed into something entirely new and exotic. The carbon that started as ice in the outer disk ended up as a diamond mantle under immense pressure, all because of a gravitational nudge that sent the planet on a journey to hell. So, after that violent birth and migration, what exactly would you experience if you could somehow stand on the surface of 55 Cancri A? The short answer is, you would be vaporized in an instant, because the surface conditions are arguably the most hellish we have ever conceptualized. This is not a planet of gentle landscapes or even harsh deserts. It is a diamond hell under skies of incandescent lava. The temperature on the day side is so extreme it defies everyday comparison, reaching up to 2,700 degrees Celsius. That is hot enough to melt iron, nickel, dot, and even most rocks, turning them into vapor. If you thought the surface of Venus was bad, this is orders of magnitude worse. The very concept of ground here is alien. Instead of solid rock, the surface is likely a global, bubbling ocean of lava, but not the silicate lava we see on Earth or Io, because the planet is so carbon-rich. This lava is probably composed of carbonates, graphite, dot, and other carbon-based compounds, all swirling in a superheated, molten state. Imagine a vast, blackish-orange sea constantly churning, with waves of liquid carbon sloshing against a shore that might be a solid crust of diamond. Yes, beneath this ocean of fire, there could be a substrate of solid diamond, the planet's thick mantle exposed or just below the surface. The pressure from the overlying layers and the intense heat create an environment where diamond is stable. But the surface itself is too hot for solid diamond to exist without melting or transforming. The planet is so close to its star that it is tidally locked, meaning one hemisphere, the day side, is permanently cooked in blinding stellar light, while the other, the night side, faces the eternal cold of space. However, cold is a relative term. The night side is still incredibly hot, likely hundreds of degrees Celsius, because some heat might be transported from the day side through atmospheric circulation or within the planet itself. The temperature difference between the two sides is dramatic, creating a colossal thermal gradient that could drive supersonic winds if any atmosphere exists to carry them. But that is a big if. The atmosphere of 55 Cancri A is a key part of its infernal character. Observations suggest it has either no significant atmosphere at all or a very thin, tenuous one, possibly composed of vaporized elements from the surface, like sodium, potassium, dot, silicon monoxide, dot, or even carbon gas. This lack of a buffering atmosphere means there is no protection from the star's relentless radiation. Ultraviolet and X-ray photons bombard the surface unimpeded, sterilizing any potential for chemistry that could lead to life. The stellar wind, a stream of charged particles, likely scours the surface directly, further eroding any attempt at atmosphere formation. Without an atmosphere, there is no weather as we know it, no clouds, no rain, just the stark, brutal exchange of radiation and heat. The sky on the day side would be a terrifying sight, an enormous, glaring star dominating the heavens, many times larger than our sun appears from Earth, blazing with an intensity that would instantly destroy any organic material. The air, if you could call it that, might shimmer with heat haze from the vaporized rock and carbon, but it would be unbreathable and scorching hot. On the night side, the sky would be pitch black, with no appreciable atmosphere to scatter light, so the stars would be visible, but the ground would still be glowing with residual heat, perhaps with a dull red glow from cooling lava or thermal radiation. The surface pressure is another unknown, but without a thick atmosphere. It might be very low, which could affect the state of the lava ocean, potentially allowing for more violent boiling and splattering. The geology here is driven by carbon, not silicates. There might be carbon-based volcanism, where lava of molten carbon compounds erupts from vents, or cryovolcanism is impossible due to the heat. The diamond crust itself might be rigid, but it could fracture under stress, creating faults and rifts filled with incandescent lava. The high gravity, more than twice that of Earth, would make any geological features appear flatter and more subdued, as it would crush mountains and limit topographic relief. The lava ocean would have incredibly high viscosity or low viscosity depending on its exact composition, but it would be in constant motion due to convection currents driven by the immense heat from below and from the star above. The transition zone between the day side and night side, the terminator, would be a place of extreme thermal stress, where temperatures change rapidly over a short distance. This could lead to interesting phenomena, like solidification of lava into strange shapes on the night side edge, only to be remelted as the planet rotates slightly or as heat flows. However, because the planet is tidally locked, this terminator is fixed, creating a permanent twilight zone that is still furnace-like but might have slightly less intense radiation. But do not imagine any respite. It is still far too hot for any known material to exist in a solid state for long. The radiation environment is lethal. Beyond the ultraviolet and X-rays, the star likely emits frequent flares, which would bathe the planet in even more intense radiation, potentially stripping away any temporary atmosphere that might form from outgassing. This constant irradiation would also break apart any complex molecules, ensuring that no prebiotic chemistry could ever take hold. The surface is thus not only inhospitable but actively destructive. Any spacecraft or probe attempting to land would be melted, vaporized, and irradiated beyond recognition within seconds. The materials we use for heat shields on Earth, like ceramics or ablative coatings, would be utterly inadequate here. The heat flux is so high that it challenges our very understanding of material science. From a distance, if we could see it, the planet might appear as a dim, reddish dot when transiting its star, but measurements of its thermal emission show it is incredibly bright in the infrared, glowing with the heat of its own creation and stellar bombardment. The day side is probably a uniform, blazing bright surface, while the night side might have a patchwork of cooler and hotter areas, depending on lava flows and thermal conductivity. The lack of atmosphere means there is no sound propagation, so the surface would be eerily silent, save for the vibrations from geological activity or the faint hiss of vaporizing material. The concept of time is also warped here. A year is only 18 hours long, so the star moves rapidly across the sky on the day side. But since it is tidally locked, It does not move at all from a fixed point on the surface. It just hangs there, forever. On the night side, the sky is static, with the same stars visible for eternity, unless the other planets in the system pass by, but they would be faint compared to the primary star. The overall impression is one of a world that has been forged in a cosmic furnace and left to bake, a testament to the extreme environments that can exist in the universe. It is a diamond world not of beauty, but of brutal, unyielding conditions that push the limits of what we consider a planet. Studying these conditions helps us appreciate the delicate balance that makes Earth habitable and reminds us that the universe is full of wonders that are utterly alien and often hostile. The surface of 55 Cancri A is the final product of its journey, a place where carbon dot, the element of life on Earth, is locked in a dead, crystalline structure, trapped under a sky of fire. It is a sobering reminder that habitability is rare and precious, and that the cosmos has many faces, most of them far from friendly. That relentless, fixed position of the sun in the sky is a direct consequence of one of the planet's most defining and extreme features, its incredibly fast orbit and the resulting tidal lock. The orbital dynamics of 55 Cancri E are not just a minor detail. They are the engine that drives its entire hostile environment. This planet completes a full journey around its star in just about 18 hours. Let that sink in for a moment. An entire year, from one spring to the next, passes in less than a single Earth day. This breathtaking speed is a simple, direct result of its proximity to the star. It orbits so close that the gravitational pull is immense, forcing the planet to whip around at a tremendous velocity just to avoid falling in. The distance is a mere 0.015 astronomical units. To put that in perspective, Mercury, the innermost planet in our solar system, is about 25 times farther from our Sun. This means 55 Cancri E is orbiting within a stellar embrace so tight it defies comparison to anything in our own cosmic neighbourhood. Such an intimate distance comes with profound consequences, the most significant being tidal locking. The gravitational forces from the star are so strong and uneven across the planet's diameter that they have effectively put the brakes on its rotation. Just as our moon always shows the same face to Earth, 55 Cancri E always shows the same face to its star. This phenomenon, known as synchronous rotation, creates a world permanently divided into two starkly different hemispheres. One side, the day side, is locked in perpetual, blazing daylight. It is a permanent front row seat to the stellar furnace, receiving a constant, unending torrent of radiation and heat. The other side, the night side, is condemned to an eternal, deep freeze. Well, not a freeze by our standards, but a relative cold that is still hundreds of degrees Celsius, yet dramatically cooler than the incandescent day side. This creates a thermal dichotomy that is almost unimaginable. The temperature difference between the two sides is not just a few degrees. It is a chasm of thousands of degrees. This fixed arrangement has dictated everything about the planet's evolution and current state. The day side is so hot that most materials would exist as vapor or a superheated liquid, likely manifesting as a global ocean of lava. The night side, while still incredibly hot, might be cool enough for a solid crust to form, perhaps a rigid landscape of graphite and other carbon allotropes, constantly radiating its heat into the blackness of space. This permanent temperature gradient could, in theory, drive ferocious weather patterns if there were a substantial atmosphere. Imagine winds screaming from the scorching day side to the cooler night side, attempting to equalize the impossible temperature difference. However, the planet's thin or non-existent atmosphere likely prevents such global storms. but it might allow for supersonic winds in the tenuous gases that could be present. The tidal forces themselves are not just a historical event that caused the locking. They are an ongoing process. The star's gravity pulls slightly more on the closer side of the planet than the far side, creating a slight bulging effect. This constant gravitational kneading pumps energy into the planet's interior, contributing to its internal heat. This tidal heating could help maintain a molten interior, potentially driving geological activity like the carbon-based volcanism we speculated about earlier. It is an extra source of heat beyond the stellar radiation and the planet's own residual formation energy. The orbit itself is also likely very stable now, a result of the system having settled into this configuration over billions of years. The other planets in the system, particularly the gas giants, have their own gravitational influences, but from their much greater distances, they cannot disrupt the tight, locked embrace between 55 Cancri A and its star. This orbital setup also makes the planet a prime target for observation. Its short year means transits happen frequently, giving astronomers many opportunities to observe it crossing the face of its star. This allows for precise measurements of its radius and studies of its atmosphere, or lack thereof, by analysing the starlight that filters through its limb. The rapid orbit also means we can study phase curves, changes in its brightness as it goes through its phases like a moon, from full dayside illumination to a thin crescent when we mostly see the night side. These phase curve observations from telescopes like Spitzer have been instrumental in mapping the temperature difference between the two hemispheres, directly confirming the predictions of tidal locking. From the surface of the day side, the star would appear gigantic, covering a significant portion of the sky, a blinding, never-setting sun. There would be no concept of sunrise or sunset, no daily cycle. Time would be measured only by the year, a frantic 18-hour cycle of day, but a day without change in light. On the night side, the star would never rise. The only light would come from the other planets in the system, which would appear as very bright stars, and the faint glow of the Milky Way, visible in the absence of an atmosphere, the terminator line, the border between day and night, would be a permanent, sharp division, a twilight zone of immense thermal stress where temperatures plummet over a relatively short distance. This region might be geologically active, with materials constantly expanding and contracting, cracking and melting. The 18-hour orbit also means the planet is moving at a staggering speed through space. This velocity, combined with its proximity to the star, subjects it to an intense stellar wind and a barrage of high-energy particles. This constant assault is a key reason why the planet cannot hold on to a substantial atmosphere. Any gases are quickly stripped away and blown into the void. The tidal locking, therefore, is not an isolated curiosity but the key that unlocks the understanding of the planet's climate, its geology, and its very surface conditions. It explains why one side is a molten hell and the other is a solid, dark landscape. It explains the extreme temperature variations we detect from Earth. It is a classic example of how a single orbital parameter, proximity, can cascade into a series of consequences that define the entire nature of a world. In the grand scheme of the galaxy, such close orbiting, tidally locked planets may be common, especially around cooler stars, but 55 Cancri E remains one of the most extreme examples. A world where a year is a blink of an eye and the sun never moves in the sky. A testament to the powerful and predictable laws of physics operating in an alien environment. Its orbit is its destiny, locking it into an eternal dance with its star. A dance of fire and darkness that will continue for billions of years to come. The perpetual blast furnace of the day side and the relative deep freeze of the night side, a direct result of that incredibly tight orbit, lead us to one of the most puzzling and actively debated aspects of this world. What, if anything, fills the space above its surface? The question of whether 55 Cancri A has an atmosphere at all is a story of scientific revision and a testament to the challenges of observing such a distant and extreme environment. Initially, data from the Spitzer Space Telescope hinted at something surprising. When scientists analysed the planet's thermal emissions, the pattern suggested the presence of a relatively thick atmosphere, one potentially rich in water vapour. This was a baffling idea for a world so close to its star, but it was a legitimate interpretation of the data available at the time. It suggested that perhaps this diamond world somehow held onto a substantial gaseous envelope, which would have profound implications for its heat distribution and surface conditions. However, science is self-correcting, and as more advanced instruments like the Hubble Space Telescope turned their gaze towards the planet, that initial picture began to fall apart. The more precise observations from Hubble failed to confirm the signatures of a thick atmosphere. Instead, the data was consistent with a very different, and in many ways more extreme, scenario. The current prevailing hypothesis is that 55 Cancri E possesses either a very tenuous, wispy atmosphere or no significant atmosphere whatsoever. This isn't a blanket of air like we have on Earth. If it exists, it's likely a transient shroud of vaporized rock. Think of it as the steam rising from a hot road after a summer rain, but on a planetary scale and composed of elements like sodium, potassium, dot, and silicon monoxide, dot, all boiled off from the superheated surface. Alternatively, the planet might be completely bare, a naked ball of diamond and lava exposed directly to the vacuum of space and the full fury of its star. The reason for this atmospheric poverty isn't hard to fathom. The planet's proximity to its star means it is subjected to an onslaught of high-energy radiation and a powerful stellar wind. Any substantial atmosphere that the planet might have formed with in its youth, perhaps a primordial envelope of hydrogen and helium, would have been quickly and relentlessly stripped away by this constant bombardment. The star's gravity also plays a role, pulling more strongly on the planet's close side and helping to tear any gaseous layer apart. This process of atmospheric erosion is likely why we see no evidence for a thick, insulating blanket. The intense heat also means that any gases present would have very high thermal velocities, making it easier for them to achieve escape velocity and drift off into space. Studying this elusive atmosphere, or the stark lack of one, is far from an academic exercise. It serves as a critical window into the planet's composition and active processes, the specific elements detected, or not detected, in any residual atmosphere can tell us directly what the surface is made of. For instance, finding signatures of silicon monoxide would point to a silicate component being vaporized, while a lack of such signals would reinforce the carbon-dominated world model. Furthermore, the presence or absence of an atmosphere directly impacts the planet's thermal profile. The vast temperature difference between the day and night sides, which we can measure from Earth, is a direct consequence of there being no substantial atmosphere to transport heat from the hot side to the cold side. If a thick atmosphere were present, it would circulate and homogenize the temperatures, much like Venus's atmosphere does, albeit to a lesser extent. The fact that we see such a sharp thermal gradient is itself strong evidence for an extremely thin or non-existent atmosphere. This makes 55 Cancri E a natural laboratory for studying atmospheric evolution under the most extreme conditions imaginable. It tests the limits of our models for how planets lose their air and what kinds of atmospheres can persist in such hostile environments. The initial misinterpretation from the Spitzer data is a classic example of how in astronomy, especially exoplanet science. Early results can be ambiguous. Spitzer's instruments were fantastic for their time, but they lacked the spectral resolution and precision of later telescopes like Hubble. The signal that looked like it could be from water vapor might have been caused by other phenomena, such as complex patterns of heat emission from a lava ocean without any air at all. This highlights the importance of follow-up observations with ever more sensitive technology. The debate isn't entirely settled, though. Some scientists still investigate the possibility of a thin, outgassed atmosphere that is constantly being replenished by geological activity from the planet's interior. If 55 Cancri E has any ongoing volcanism or outgassing, it could be slowly releasing gases that form a temporary, localized atmosphere, which is then just as quickly destroyed by the stellar wind. This would create a dynamic equilibrium where the atmosphere is always there, but always thin and patchy. Observing such a thing is incredibly difficult from 40 light-years away. The methods used to probe the atmosphere are ingenious but require immense precision. The primary technique is transmission spectroscopy, when the planet transits, or passes in front of its star from our perspective. A tiny fraction of the starlight filters through the planet's limb, the thin ring of its atmosphere. By analysing the spectrum of that filtered light, astronomers can look for absorption features, specific wavelengths where atoms or molecules in the atmosphere have absorbed the starlight. Each element and molecule has a unique fingerprint. For 55 Cancri E, these searches have so far yielded no clear, definitive detections of common atmospheric gases. This null result is, in itself, a powerful piece of data. It rules out certain types of atmospheres and pushes us toward the thin or none model. Another method is to look at the planet's emission spectrum, the light it gives off directly, particularly from its night side. The temperature and composition of the night side can reveal whether an atmosphere is trapping heat or not. The observed coldness of the night side is another nail in the coffin for a thick atmosphere. The James Webb Space Telescope is poised to revolutionize this investigation. Its unparalleled sensitivity in the infrared will allow it to search for these atmospheric signatures with a precision never before possible. It might be able to detect the faint spectral lines of those vaporized rock elements, finally confirming the existence of a tenuous shroud. Or it might confirm the absolute absence of any atmosphere, solidifying the picture of a bare, scorched world. This isn't just about one planet. It's about understanding a whole class of worlds. Many exoplanets discovered are close-in super-Earths, and 55 Cancri E is a key case study for what happens to such planets in extreme environments. Its atmospheric story informs our predictions about other similar worlds. If a planet with twice Earth's mass and 8 times its mass cannot hold onto an atmosphere this close to a sun-like star, that tells us something fundamental about planetary formation and evolution. It also has implications for the concept of habitability. An atmosphere is a key ingredient for life as we know it, providing pressure, temperature regulation, and a medium for chemistry. The apparent lack of one on 55 Cancri E is the final seal on its status as an utterly sterile world. It completes the picture of an environment where not even the simplest building blocks of life could survive, let alone evolve. The search for its atmosphere is therefore a search for understanding the boundaries of planetary existence. It's a detective story where the suspect, the atmosphere, might have fled the scene entirely, and we're left piecing together the clues from the aftermath. Each observation, each new data set, brings us closer to a definitive answer, teaching us not only about this particular diamond hell, but about the physics that governs all planets under fire. The stark reality of a world with no atmosphere to speak of brings us to perhaps the most profound implication of 55 Cancri E, what it tells us about the search for life beyond Earth. While the discovery of such an exotic planet expands our imagination and understanding of planetary diversity, it also serves as a powerful, sobering lesson in why the mere presence of elements essential for life is nowhere near sufficient for biology to arise. This carbon-rich world, ironically, is one of the most hostile environments conceivable for life as we know it. The very element that is the backbone of all known biological molecules, carbon, is present here in staggering abundance, but it is trapped in a form that is utterly inert and unavailable for the complex chemistry of life. On Earth, carbon is a versatile player, forming long chains and rings that build proteins, DNA, and sugars, all dancing in the solvent of liquid water. But on 55 Cancri E, the carbon is locked away in a rigid, crystalline lattice of diamond, a structure that is chemically stable and unreactive under these conditions. It is a cosmic irony. The element of life is present in its purest, most pristine form, yet it is completely dead, unable to participate in the dynamic molecular interactions that define living systems. The second critical ingredient for life, liquid water, is impossible here. The surface temperatures are so extreme that they far exceed the critical point of water. Water cannot exist as a liquid. It would instantly dissociate into hydrogen and oxygen, or simply be vaporized into a superheated gas. Without a liquid solvent, the complex chemical reactions that lead to self-replication and metabolism cannot occur. The molecules of life need a medium to move, collide, and interact. And that medium, for all life on Earth, is water. The absence of this universal solvent is a deal breaker. Furthermore, the intense heat itself is destructive. The surface temperatures are high enough to melt iron and vaporize rock. Any complex organic molecule, no matter how robust, would be torn apart by the thermal energy long before it could form any kind of stable structure. The bonds that hold together amino acids, nucleotides, and lipids would be shattered instantly. The environment is not just inhospitable, it is actively destructive to the very building blocks of life. Adding to this inferno is the relentless radiation bath. With little to no atmosphere to act as a shield, the planet's surface is bombarded by the full spectrum of electromagnetic radiation from its star, including high-energy ultraviolet and X-rays. These photons carry enough energy to break chemical bonds and ionize atoms, effectively sterilizing the surface and preventing any nascent prebiotic chemistry from taking hold. Even if by some miracle a complex molecule formed, it would be rapidly destroyed by this radiation. The stellar wind, a stream of charged particles, continuously scours the surface, further ensuring that no fragile chemical network could ever establish itself. The tidal locking of the planet creates another layer of impossibility. While the night side is cooler, it is still far too hot for life, and it is shrouded in perpetual darkness, receiving no energy from the star to drive any potential photosynthetic processes. The day side, while flooded with energy, is too energetic, destroying rather than nurturing. There is no Goldilocks zone on this planet, no region where conditions are just right. The planet's high gravity also poses a problem, though a minor one compared to the heat and radiation. It would compress any potential chemical environment and make movement and diffusion of molecules more difficult, though this is negligible compared to the other showstoppers. The lack of a geochemical cycle like the carbon cycle on Earth further seals its fate. On Earth, plate tectonics and other geological processes recycle elements and help regulate the climate. On 55 Cancri A, the geology is likely stagnant, with a rigid diamond mantle preventing the kind of dynamic interior that could support a long-term stable environment. All of these factors combine to paint a picture of a world that is not only barren, but fundamentally antagonistic to the very concept of life. This has profound implications for how we search for habitable exoplanets. 55 Cancri E teaches us that we cannot simply look for planets that are Earth-sized or located within the traditional habitable zone of their star. We must also consider the stellar environment, the planet's atmospheric composition and retention, its geological activity, and most importantly, the fundamental chemistry of the system. A star with a high carbon-to-oxygen ratio might be a red flag for Earth-like life, as it could lead to the formation of carbon planets like this one, where the chemistry is all wrong for biology as we understand it. It reinforces the idea that habitability requires a delicate and rare balance of many factors: a stable orbit within a temperate zone, the presence of a solvent like water, a protective atmosphere, a suitable chemical inventory, and a source of energy that is not too intense. 55 Cancri E possesses none of these. It is a testament to the fact that the universe is vast and full of wonders, but the specific conditions that allow for the emergence of life are exceptionally fine-tuned. This does not mean that life is impossible elsewhere. It simply means that we must broaden our definition of life while also recognizing that the parameters for its existence are likely very narrow. The study of this diamond world helps us refine our search strategies. It tells us that when we look at the atmospheric spectra of exoplanets, we should not only look for biosignatures like oxygen and methane, but also for anti-biosignatures, like the presence of carbon monoxide or the absence of water vapour, which could indicate a hostile, carbon-dominated world. It also highlights the importance of studying the host star's composition, as that is the ultimate blueprint for the planets that form around it. In the end, 55 Cancri E is a cosmic lesson in humility. It shows us that our Earth is a rare and precious gem in its own right, not for its diamonds, but for its life. The planet's existence expands the catalogue of planetary possibilities, but it also sharply defines the boundaries of the habitable. It is a reminder that the universe is capable of creating astonishing beauty and extreme hostility in equal measure, and that the search for life is a search for needles in a cosmic haystack filled with both promise and peril. Understanding why worlds like this are dead helps us appreciate why our own world is alive, and it guides our telescopes towards other stars where the conditions might be just a little more like home, while the search for life teaches us about the delicate balance required for biology. The very phrase "diamond planet" inevitably triggers a more primal reaction, the allure of unimaginable wealth. It is a concept that captures the public imagination, fueling dreams of cosmic treasure troves and futuristic mining operations. However, the economic reality of a world like 55 Cancri A is a sobering antidote to such science fiction fantasies. Let us be perfectly clear. The idea that this planet represents any kind of financial windfall is a profound misunderstanding of both economics and interstellar logistics. The value of a diamond on Earth is an artificial construct, meticulously maintained by its relative rarity, controlled mining output, and deep-rooted cultural appeal for its brilliance and durability. It is a value built on scarcity and perception, on a world where diamonds are not rare gems, but a fundamental geological component. That entire foundation collapses if you have a planet where trillions upon trillions of carats exist as common rock. The material instantly loses all its scarcity-based commercial value. It would be like trying to sell sand in the middle of a desert. The material is functionally worthless because it is everywhere. The very act of retrieving even a single diamond from this world would be an endeavour of such monumental cost and complexity that it completely dwarfs any potential return. The planet is located 40 light-years away from Earth. To grasp the scale of that distance, Consider that light itself, the fastest thing in the universe, takes 40 years to travel from there to here with our current technology. A spacecraft like Voyager would take over 500,000 years to reach it. Even if we imagine a future propulsion system that could achieve a significant fraction of light speed, say 10%, the journey would still take 400 years one way. The energy required for such a mission is beyond comprehension, requiring fuel sources and engineering we can scarcely dream of today. The spacecraft would need to be a self-sustaining ark, surviving centuries in the void, only to arrive at a destination that is itself a death trap. The mining operation on the planet's surface would be a nightmare of epic proportions. The surface gravity is more than twice that of Earth's, meaning every piece of equipment would be crushingly heavy. The temperature is hot enough to melt iron and vaporize most metals, so any mining machinery would have to be built from materials that can withstand thousands of degrees Celsius, perhaps active cooling systems that would require even more energy. The surface itself might be a global ocean of lava, or a solid crust of diamond so hard that conventional drilling is impossible. And for what? To extract a material that, once brought back in bulk, would have no market value because its abundance would have destroyed the very concept of diamond as a precious gem. The entire diamond industry on Earth is built on the careful control of supply. If a starship returned with even a small asteroid's worth of diamond, it would flood the market, causing the price to plummet to zero. The economic incentive simply does not exist, while the costs are astronomically prohibitive, and the payoff is self-defeating. This is not to say that diamond would have no uses. Its industrial applications for cutting and drilling are well known, but for those purposes, we can already create synthetic diamonds cheaply and efficiently in labs on Earth. There is no need to travel 40 light years for an industrial abrasive. The logistical challenges extend beyond just getting there and mining. The transportation of the mined material back to Earth would require even more energy. You would need a colossal spacecraft with immense fuel reserves to carry a payload of diamond, which is incredibly dense, back across that vast interstellar gulf. The communication lag alone, at 80 years for a round-trip message, makes any real-time control of remote operations impossible. Every step of the process, from navigation to mining to return, would have to be entirely autonomous, capable of handling countless unforeseen problems over a timescale of centuries. This is not a business venture. It is a multi-generational, civilization-level project with no economic return on investment. The true value of 55 Cancri A is not material. It is scientific and philosophical. Scientifically, it is a Rosetta Stone for understanding planetary formation. Its existence proves that planets can be made from completely different recipes than those in our own solar system. It forces us to expand our models and consider carbon worlds as a distinct class, studying its composition, orbit, and atmosphere, or lack thereof, provides critical data on how planets behave under extreme conditions, informing our search for an understanding of all exoplanets. Philosophically, it holds up a mirror to our own values. It challenges our anthropocentric notions of wealth and rarity. On a cosmic scale, a diamond is just a specific arrangement of carbon atoms, common under the right conditions of pressure and heat. Our perception of it as precious is a purely human invention. The planet symbolizes the humility we must learn when thinking on a galactic scale. What we consider a treasure on our small world is a mundane building block in another. It teaches us that the real riches of the universe are not found in inert crystals, but in knowledge, understanding, and the profound mystery of existence. The energy and intellect required for a mining mission would be far better spent on projects that enhance our life on Earth or further our scientific exploration of the cosmos in a meaningful way. Sending probes to study its atmosphere and composition from afar yields immense scientific value without the futile expense of retrieval. The concept of a diamond planet, therefore, serves as a powerful thought experiment. It separates the fantasy of science fiction from the hard realities of physics and economics. It reminds us that value is not an intrinsic property of matter but is assigned by societies and markets. In the void between stars, a diamond has no more inherent value than a chunk of granite. The legacy of 55 Cancri A will not be a new era of space mining wealth. It will be a deeper appreciation for the diversity of worlds and a clearer understanding of our own place in the universe. It shows us that the cosmos is full of wonders that can expand our minds without filling our pockets, and that sometimes the most valuable discoveries are the ones that teach us what not to pursue. The dream of exploiting such a world is a diversion from the real prize. The knowledge gained from simply knowing it exists and understanding what it tells us about the universe. So, while the headlines may scream about a planet of diamonds, the sober truth is that its greatest gift to us is the perspective it offers. A lesson in cosmic economics where the balance sheet is measured in insight, not income. The journey from a speculative idea to a well-characterized diamond world was not possible with the naked eye or simple telescopes. It required a revolution in astronomical technology and technique. The story of how we uncovered the secrets of 55 Cancri E is a story of ingenious methods and powerful instruments working in tandem. It began with the radial velocity method, a technique that doesn't look for the planet directly, but instead watches for the subtle telltale wobble it imposes on its star. The planet's gravity, as it orbits, pulls the star back and forth, causing a tiny shift in the colour of the star's light due to the Doppler effect. This is an incredibly subtle measurement. For a planet like 55 Cancri A, the star's movement is a mere walking pace, a shift of a few meters per second. Detecting this required spectrographs of phenomenal precision, like the Hires instrument on the Keck telescope in Hawaii. These devices can split the light from a star into a very detailed spectrum, a rainbow of colours, and measure minute changes in the position of specific spectral lines. Years of persistent observation of the star 55 Cancri A revealed a complex pattern of wobbles, which astronomers painstakingly decoded to infer the presence of multiple planets, with the signature of the innermost world, Planet E, finally being confirmed in 2004. This gave us the planet's mass and orbital period, but it was only half the picture. The next major breakthrough came from the transit method. This involves monitoring the brightness of a star with extreme precision, watching for the tiny dip that occurs when a planet passes directly in front of it, blocking a small fraction of the starlight. For 55 Cancri E, this dip is minuscule, less than 1/5 of the star's total light. Detecting this was the work of space telescopes, which operate above the distorting effects of Earth's atmosphere. The Canadian MOST space telescope was one of the first to successfully observe transits of 55 Cancri E, followed by the much more sensitive Spitzer space telescope. Spitzer, observing in the infrared, was particularly crucial. The transit provided the planet's radius. When you combine the planet's mass, known from the radial velocity wobble, with its radius, known from the transit, you get its density. This was the critical number, the revelation that this was no ordinary world. The high density was the first major clue that pointed towards an exotic, carbon-rich composition. But the technological story did not end there. Spitzer also allowed for phase curve observations. Since the planet is so close to its star, it exhibits phases, much like our moon. By measuring the combined light of the star and the planet over a full orbit, scientists could separate out the tiny amount of infrared light coming from the planet itself. This allowed them to map its temperature, confirming the extreme heat of the day side and the relative coolness of the night side, which in turn provided strong evidence for tidal locking and a lack of a substantial atmosphere. The investigation into its atmosphere required yet another set of tools. The Hubble Space Telescope, with its sensitive spectrographs, attempted to use transmission spectroscopy. During a transit, a tiny fraction of the starlight filters through the planet's atmosphere, if it has one. Atoms and molecules in the atmosphere absorb specific wavelengths of this light, creating a fingerprint. Hubble's observations, however, found no such fingerprints for water vapor or other volatile gases, pushing the consensus towards a thin or non-existent atmosphere. Each of these methods has its strengths and limitations. The radial velocity method is great for finding massive planets close to their stars and measuring their mass, but it tells you nothing about the planet's size or composition. The transit method gives you the radius and, when combined with mass, the density dot, but it only works for planetary systems that are aligned edge-on from our viewpoint. Spectroscopy of atmospheres is incredibly challenging and is only possible for the brightest and closest systems. The characterization of 55 Cancri E was a masterpiece of combining these techniques. It showed the power of multi-method astronomy. The initial discovery was made with ground-based telescopes using radial velocity, but the detailed characterization required the stable, precise environment of space. Now, the torch is being passed to a new generation of instruments. The James Webb Space Telescope represents a quantum leap in capability. Its large mirror and sophisticated infrared instruments are perfectly suited for studying a hot, nearby world like 55 Cancri E. Webb can take phase curve measurements with unprecedented precision, potentially mapping temperature variations across its surface. It can perform transmission spectroscopy with much higher sensitivity, perhaps finally detecting the spectral signatures of vaporized rock like silicon monoxide, or confirming the absolute absence of any atmosphere. It might even be able to detect thermal emission from the surface directly, giving us clues about whether it is a solid crust or a global lava ocean. The technological evolution is continuous. Future missions, like the planned Habitable Worlds Observatory, will build on these techniques, pushing the sensitivity even further. The story of 55 Cancri E's detection is a testament to human ingenuity. It is about measuring the almost immeasurable, a wobble the speed of a walking person in a star 40 light-years away, a dip in brightness smaller than the shadow of a gnat flying in front of a car headlight, and the faint heat signature of a world glowing in the dark. These are not simple observations. They are the result of decades of engineering advancement, sophisticated data analysis, and international collaboration. The instruments are the extensions of our senses, allowing us to reach across the light years and touch, in a metaphorical sense, the diamond heart of a distant world. They transformed 55 Cancri A from a mere gravitational blip into a complex, characterized world with a known size, mass, density, temperature map, and constrained atmospheric properties. This technological journey is far from over. Each new telescope and each new method will peel back another layer, revealing more secrets about this extraordinary planet and the countless others waiting to be discovered. The tools that revealed 55 Cancri A have not only told us its story, but have also paved the way for how we will study and understand the next generation of exoplanets. bringing us closer than ever to answering the age-old question of whether we are alone in the universe. The incredible technological leap that allowed us to find and measure 55 Cancri A now lets us ask an even more intriguing question. What is happening beneath its surface? What does the geology of a diamond world actually look like? This is where we move from detection to imagination grounded in physics, painting a picture of an exotic planetary interior that operates under rules completely alien to our own. On Earth, our geology is dominated by silicate rocks, water, and plate tectonics. But on 55 Cancri A, the entire system is based on carbon. The prevailing model suggests that deep inside, this planet has a core, likely composed of iron and perhaps some silicon, similar to Earth's core but probably smaller in relative size. Surrounding that core, however, is not a mantle of molten rock, but an immensely thick layer of diamond. This isn't a thin vein. We are talking about a mantle hundreds or even thousands of kilometers deep, made primarily of crystallized carbon. This diamond mantle is the key to the planet's high density and its rigid internal structure. The conditions there are extreme, with pressures millions of times greater than Earth's atmosphere and temperatures soaring to thousands of degrees. Yet diamond remains stable, forming a solid, superheated layer that behaves very differently from the rocky mantle of our world. Above this diamond mantle, the models suggest there could be a crust, but it's not made of granite or basalt. It's likely composed of graphite, another form of carbon. Under the intense pressure of the overlying layers, graphite is stable, but if geological processes bring material to the surface where pressure is lower, it might transform into other allotropes, though the surface heat probably keeps everything in a state of constant change. This layered structure, iron core, dot, diamond mantle, graphite crust, is the foundational geological model for this carbon super-Earth. Now, what about geological activity? Does this planet have volcanoes? The answer is probably yes, but they would be nothing like the volcanoes on Earth or Io. With the interior rich in carbon and other elements, the magma or molten material could be composed of carbonates, sulfides, or even superheated silicon carbide. Instead of silicate lava, you might have carbonatitic lava, which could be less viscous and erupt in different ways. These hypothetical volcanoes would spew forth rivers of molten carbon compounds, creating landscapes of congealed carbon-based rocks. The driving force for this volcanism could be the immense internal heat from the planet's formation and radioactive decay, combined with tidal heating from its star. The extreme temperature difference between the permanent day side and night side might also create massive convection currents within the diamond mantle itself. Even though diamond is incredibly hard, under those temperatures and pressures, it can actually flow and convect over geological timescales. This convection could be the engine that drives this exotic volcanism, pushing molten carbon material up through fractures in the rigid outer layers. However, the concept of plate tectonics as we know it is almost certainly absent. Plate tectonics on Earth requires a lithosphere that can break into plates and an underlying asthenosphere that is ductile enough to allow for movement. On 55 Cancri E, the diamond-rich lithosphere is likely too strong and rigid to fracture into plates. Diamond has a very high shear strength, making it resistant to the kind of brittle failure that initiates subduction zones on Earth. So, instead of a dynamic system of moving plates, the geology might be more static, dominated by vertical tectonics like upwelling from mantle convection and downwelling, but no horizontal plate motion. This could lead to a surface with large, stable regions and localized areas of volcanic activity, but no continental drift or oceanic spreading centers. The surface itself is probably a geologically young and active place. Despite the lack of plate tectonics, The constant bombardment of stellar energy and the internal heat likely keep the crust in a state of continual renewal. On the day side, where temperatures are high enough to melt most materials, the surface might be a global ocean of carbon-rich lava, constantly churned by convection and possibly by tides from the star's gravity. This lava ocean could have its own cycles of solidification and remelting, especially near the terminator line where temperatures drop sharply. On the night side, the crust might be solid and thick, but still hot, with possible cryovolcanism completely absent due to the heat. The geology is also influenced by the planet's high gravity, with surface gravity more than twice that of Earth. Any topographic features like mountains would be limited in height. The high pressure would compress the crust, making it denser and potentially reducing the frequency of large-scale faulting. Any mountains that did form would be quickly flattened by gravitational relaxation, or they might be composed of materials with high compressive strength, like diamond itself. Imagine vast, low-lying plains of graphite, punctuated by volcanic vents oozing molten carbon, under a sky dominated by a huge, glaring star on one side and eternal darkness on the other. The lack of water and an atmosphere means there is no erosion from wind or rain, so geological features could persist for long periods, only to be altered by volcanic resurfacing or impacts. Speaking of impacts, the planet's proximity to its star might mean it is somewhat protected from comet and asteroid impacts by the star's gravity, but any impacts that do occur would be dramatic, possibly excavating material from the diamond mantle and scattering it across the surface. The geological models are constantly being refined as new data comes in. Observations from telescopes like Spitzer and Hubble, and future data from the James Webb Space Telescope can provide clues. For instance, measuring the heat flow from the planet's interior or detecting specific gases in any transient atmosphere could tell us about ongoing volcanic outgassing. If we were to detect signs of silicon monoxide or carbon dioxide, it might indicate active volcanism recycling the crust. The study of 55 Cancri E's geology is not just about understanding one world. It's about expanding our knowledge of planetary science. It shows that the principles we derived from studying Earth and other solar system bodies are not universal. A planet can have a mantle of diamond, volcanoes that erupt carbon lava, and a tectonic system that is utterly stagnant. This forces geologists to think outside the box and consider how common processes like mantle convection and volcanism manifest in entirely different chemical environments. The models for 55 Cancri E serve as a template for other carbon-rich planets we might discover. They help us interpret data from other exoplanets and predict what kinds of geological activity might be possible. For example, if we find a planet with a similar density and stellar context, we might immediately suspect a diamond interior and a lack of plate tectonics. This has implications for habitability as well. As a static, carbon-dominated geology offers no long-term climate regulation through a carbon cycle like Earth's. The planet's geology is a direct result of its formation history, born in a carbon-rich disk, migrated inward, and stripped of its volatiles, then forged into a diamond world by immense pressure and heat. Its current state is a snapshot of that ongoing process, a world where carbon is the king of elements, dictating the structure and activity from the core to the surface. Understanding these geological models is crucial because it completes the picture of 55 Cancri A, transforming it from a mere point of light into a dynamic, if hostile, world with its own unique and fascinating geological personality. The wild geology of 55 Cancri A, with its diamond mantle and carbon lava, forces us to look back at our own solar system with fresh eyes, making comparisons that highlight just how unique and special our rocky planets really are. When we place this exotic world side by side with Earth, Venus, Mars, and even Mercury, the differences are not just of degree but of fundamental nature, teaching us profound lessons about what makes a planet habitable or hellish. The most striking comparison starts with basic composition. Earth is what scientists call a silicate planet. Its bulk is made mostly of rocks rich in silicon and oxygen, with an iron core, and it is wrapped in a nitrogen-oxygen atmosphere. It has vast oceans of liquid water, an active magnetic field, and plate tectonics that recycle carbon and regulate climate. 55 Cancri E, on the other hand, is a carbon planet. Its building blocks were dominated by carbon, leading to an interior where diamond forms a significant portion of the mantle. This fundamental difference in chemistry stems from the very first stages of planetary formation. Our solar system formed from a protoplanetary disk with a specific carbon-to-oxygen ratio that favoured the formation of silicate minerals. The 55 Cancri system, however, had a much higher ratio of carbon to oxygen, meaning carbon compounds like graphite and silicon carbide were the primary solids available for planet building. This simple chemical difference in the natal cloud dictated entirely different planetary outcomes. It teaches us that the initial ingredients in a stellar system are the single most important factor in determining what kinds of planets will form. We cannot assume that every star will have Earth-like worlds. Many might have carbon-based planets like 55 Cancri A, which are inherently hostile to life as we know it. Looking at size and mass, 55 Cancri E is classified as a super-Earth, with a radius about twice ours and a mass 8 times greater. This puts it in a category that doesn't exist in our inner solar system. Mercury, Venus, Earth, and Mars are all smaller and less massive. This comparison shows that planetary systems can have a much wider variety of terrestrial worlds than our own limited sample suggests. Our solar system has a clear dichotomy: small, rocky inner planets and large, gaseous outer planets. The discovery of super-Earths like 55 Cancri E reveals that many systems have planets intermediate in size, filling a gap that our solar system lacks. This tells us that our system might be the exception rather than the rule, and that super-Earths are probably very common throughout the galaxy. The density of 55 Cancri E is nearly twice that of Earth, which immediately signals its exotic composition. Earth's density is explained by its iron core and silicate mantle. The high density of 55 Cancri E requires a material even denser than silicate rock, and diamond fits that bill perfectly. Comparing it to Venus, which is often called Earth's twin because of its similar size and mass, highlights how composition trumps size. Venus has a density very close to Earth's, indicating a similar silicate and iron composition, but its atmosphere is a thick hell of carbon dioxide with a runaway greenhouse effect. While Venus is infernally hot, 55 Cancri E is on another level, with temperatures high enough to melt its surface into a lava ocean. This shows that proximity to the star is crucial, but so is atmospheric retention. Venus held onto its atmosphere, while 55 Cancri A likely lost its due to the extreme stellar environment. Mars provides another interesting contrast. It is a small, rocky world with a thin atmosphere and evidence of past water. Its size was too small to maintain a strong magnetic field and a thick atmosphere, leading to its current cold, dry state. 55 Cancri A has plenty of mass, but its location doomed it to atmospheric loss. This teaches us that mass alone is not a guarantee of habitability. Location and stellar activity are equally critical. The orbit of 55 Cancri A is another point of extreme difference. Its year is 18 hours, and it is tidally locked. In our solar system, Mercury has the shortest year at 88 days, and it is not tidally locked to the Sun. It has a complex resonance. The fact that 55 Cancri A is locked shows the overwhelming power of tidal forces when a planet is so close. This locking creates a permanent day side and night side, a situation that doesn't occur on any planet in our solar system. Earth, with its 24-hour rotation, has a balanced day-night cycle that helps distribute heat and makes the entire planet potentially habitable. The tidal locking of 55 Cancri A ensures that one half is a perpetual furnace and the other a somewhat cooler, but still deadly, landscape. This comparison underscores the importance of a planet's rotation for climate stability. The absence of a substantial atmosphere on 55 Cancri E, compared to the thick atmospheres of Venus and Earth, is a key lesson in atmospheric evolution. Earth and Venus were able to retain their atmospheres despite solar wind because they formed at a distance where the stellar radiation was less intense. 55 Cancri E, orbiting 25 times closer than Mercury, never stood a chance. Its primordial atmosphere was likely stripped away early, leaving it bare. This tells us that the habitable zone is not just about temperature. It is also about a region where a planet can maintain a protective atmosphere against stellar erosion. The geological comparisons are equally enlightening. Earth has active plate tectonics, which drives volcanism, recycles carbon, and regulates long-term climate. Venus may have had plate tectonics in the past, but now seems to have a stagnant lid with periodic massive resurfacing. Mars is largely geologically dead. 55 Cancri A, with its rigid diamond mantle, probably has no plate tectonics at all. Its geology is likely driven by vertical tectonics and volcanism from mantle convection, but without the horizontal movement of plates. This lack of a carbon cycle like Earth's means there is no mechanism to regulate temperatures over geological timescales. On Earth, the carbon silicate cycle acts as a thermostat, drawing down carbon dioxide when temperatures rise and releasing it when they fall. 55 Cancri E has no such process, locking it into a permanent extreme state. This teaches us that a dynamic interior is crucial for long-term planetary habitability. The presence of water is another stark difference. Earth is the water world, with oceans covering most of its surface. Mars has water ice, and Venus might have had water in the past. 55 Cancri E is far too hot for any water to exist, and its carbon-dominated chemistry means water was probably never a significant component. This highlights that water, the solvent of life, is a rare and precious commodity in the universe, dependent on a planet forming in the right place with the right chemistry. The magnetic field is another point of comparison. Earth has a strong magnetic field generated by its liquid iron core, which protects the atmosphere from solar wind. Mars has a weak magnetic field, contributing to its atmospheric loss. We do not know if 55 Cancri E has a magnetic field, but given its likely solid iron core and lack of a rapid rotation, it might not. This would have accelerated the loss of any atmosphere it once had. These comparisons collectively teach us that Earth is a rare gem. It formed in a system with the right chemistry, at the right distance from a stable star, with the right size to hold an atmosphere and water, and with a dynamic interior that regulates its climate. 55 Cancri E shows us the opposite extreme, a world born from a carbon-rich disk, dragged too close to its star, stripped of its atmosphere and water, and forged into a diamond. This contrast is humbling. It tells us that while the universe is full of planets, most of them are not like Earth. The conditions for life are exceptionally fine-tuned. Every time we study an exoplanet like 55 Cancri e, we gain a deeper appreciation for our own world. It is not just a ball of rock. It is a complex, interconnected system that has maintained habitability for billions of years. The diamond world reminds us that value is not in precious stones, but in the delicate balance that allows life to flourish. It expands our definition of a planet while simultaneously narrowing the conditions for habitability. As we search for other Earths, we now know to look for stars with solar-like compositions, planets in the temperate zone, with signs of water and atmosphere, and evidence of geological activity. 55 Cancri e is a guidepost, showing us one of the many dead ends in the cosmic maze, and making the vibrant, living Earth seem all the more miraculous. After understanding how 55 Cancri e contrasts so sharply with the worlds in our own solar system, our natural next step is to look forward, to the tools that will allow us to peer even deeper into its mysteries and those of other exoplanets. The future of observing this diamond world and others like it is being revolutionized right now by a new generation of telescopes, led by the James Webb Space Telescope. This observatory is not just an incremental upgrade, it is a fundamental leap in our ability to study the cosmos, particularly in the infrared part of the spectrum. Its massive mirror, which is over 6 times the collecting area of the Hubble Space Telescope, and its suite of incredibly sensitive instruments are perfectly tailored for dissecting the light from distant worlds. For a planet like 55 Cancri e, Webb's capabilities are a game changer. One of its primary methods will be transmission spectroscopy. As the planet transits its star, a tiny fraction of the starlight filters through any atmosphere it might have. Webb can analyze this filtered light with unprecedented precision, looking for the specific absorption fingerprints of atoms and molecules, while previous telescopes like Hubble found no evidence for a substantial atmosphere. Webb's superior sensitivity might finally detect the elusive signatures of a tenuous shroud, perhaps composed of vaporized rock like silicon monoxide or even carbon-based gases. Alternatively, it could definitively confirm the absence of any atmosphere, solidifying our understanding of this bare, scorched world. Beyond just sniffing the air, Webb will excel at studying the planet's thermal emissions. It can observe the phase curve of 55 Cancri e, measuring its brightness changes throughout its entire 18-hour orbit. This will allow scientists to create a much more detailed temperature map of the planet. They will be able to precisely measure the searing heat of the permanent day side and the comparative cool of the night side, providing critical data on how heat is transported or not transported around the planet. This information is vital for understanding the surface conditions. If the temperature difference is extremely sharp, it supports the model of no atmosphere and possibly a solid surface. If there are more gradual transitions, it might hint at some form of atmospheric circulation or even the presence of a global lava ocean that redistributes heat. Webb might even be able to perform secondary eclipse spectroscopy, which involves measuring the light from the planet directly when it is eclipsed by its star, giving us a pure spectrum of its day side. This could reveal the thermal signature of the surface itself, offering clues about whether it is solid diamond, molten carbon, dot, or something else entirely. The data from Webb will not just provide snapshots. It will allow us to test and refine our models of the planet's interior structure and geology by constraining the atmospheric composition and surface temperature with far greater accuracy. We can improve our computer simulations of its diamond mantle and carbon-based volcanism. Furthermore, Webb will study the planet's host star in exquisite detail, helping us understand the stellar radiation and wind that shape the planet's environment. This is crucial for putting 55 Cancri E in its full context. But the James Webb Space Telescope is just the beginning of this new era. Its observations will pave the way for even more advanced observatories already on the drawing board. Concepts like the Habitable Worlds Observatory, a proposed large space telescope designed specifically to image and characterize Earth-like planets around other stars, will build directly on Webb's legacy. While a planet like 55 Cancri E is far from habitable, the techniques developed to study it will be refined and applied to more temperate worlds. The Habitable Worlds Observatory would aim to directly capture the light of exoplanets, separating their faint glow from the overwhelming glare of their host stars. This would allow for direct spectroscopy, where we can analyze the light from the planet itself without relying on transits. For a world as hot and bright as 55 Cancri A, this might even enable the first crude maps of its surface, revealing the distribution of hot and cold regions and potentially identifying major geological features. Other future ground-based telescopes, like the Extremely Large Telescope, with mirrors 30 to 40 meters in diameter, will also contribute. Their immense light-gathering power will allow for precise radial velocity measurements, potentially detecting even smaller planets in the system or measuring the planet's gravitational influence on its star with greater accuracy, which could reveal details about its internal density distribution. The future of observation is also about longevity and monitoring. Webb and its successors will likely observe 55 Cancri A not just once, but many times over years, looking for changes in its transit depth, its thermal emission, or its atmospheric signature. This long-term monitoring could reveal dynamic processes, such as variations in volcanic outgassing or changes in the lava ocean coverage, providing a glimpse into the active geology of a carbon world. The role of these telescopes extends beyond a single planet. They will survey many exoplanetary systems, allowing us to place 55 Cancri A in a statistical context. Is it a rare oddity, or are carbon planets common around metal-rich stars? By studying a large sample, we can understand the prevalence of such exotic worlds and the conditions that lead to their formation. The technological advancements driving these telescopes are not just about bigger mirrors. They involve sophisticated coronagraphs and starshades to block starlight, advanced cryogenics to keep infrared detectors sensitive, and complex data processing algorithms to extract the faint signals of planets from the noise. The knowledge gained from Webb's study of 55 Cancri A will directly inform the design and operation of these future missions. For instance, if Webb confirms the presence of specific molecules in a thin atmosphere, future telescopes will know what signatures to look for in other systems. The ultimate goal is to find and characterize planets that could support life, but understanding the entire spectrum of planetary possibilities, including hellish worlds like 55 Cancri A, is essential for that quest. It teaches us what to avoid and what parameters are important for habitability. The future of observation is a collaborative, international effort, with telescopes in space and on the ground working together to build a comprehensive picture of planetary systems. The James Webb Space Telescope is the powerful new engine driving this journey of discovery, and its successors will carry the torch even further, transforming points of light into worlds with known landscapes, atmospheres, and histories. The story of 55 Cancri E is far from over. With these new eyes on the sky, we are just beginning to read its chapters, and the insights we gain will reshape our understanding of our place in the universe. The incredible precision of new telescopes like the James Webb allows us to probe not just the physical conditions of worlds like 55 Cancri A, but also to confront a deeper, more philosophical paradox that this planet embodies, a puzzle known as the carbon paradox. It is a concept that highlights a strange and fascinating contradiction about our place in the universe. Carbon is one of the most abundant elements in the cosmos, forged in the hearts of stars and scattered across space by supernovae. It is also the absolute fundamental building block of life on Earth. Every protein, every strand of DNA, every cell membrane is constructed from carbon atoms. Given this cosmic abundance and biological essentiality, you would expect carbon to be everywhere on our planet, littering the surface in its pure form. But here is the paradox. On Earth, pure elemental carbon is relatively rare. We find it in a few specific places, like graphite deposits or the occasional diamond pipe. But the vast majority of Earth's carbon is not lying around as an element. It is locked away in the form of carbon dioxide in the atmosphere, dissolved as carbonate ions in the oceans, or buried as organic matter and fossil fuels in the crust and mantle. The carbon is there, but it is sequestered, hidden, and regulated. This is where 55 Cancri E serves as the ultimate cosmic contrast. This planet is a testament to what happens when carbon is not efficiently hidden away. In a system with a high carbon to oxygen ratio, the carbon was able to dominate the planetary formation process. There was no great mechanism to sequester it, to bind it into gases that could escape or be dissolved in vast oceans. Instead, it became the primary rock, the very stuff of the planet itself. Under the immense pressures in its interior, that carbon crystallized into a diamond mantle, creating a world where the element of life is frozen in a sterile, geological form. This contrast teaches us a critical lesson about habitable worlds. The Earth, paradoxically, is a carbon-poor planet in terms of its surface rocks, and that is precisely why it is a life-rich planet. Our planet has a sophisticated and dynamic carbon cycle, a planetary thermostat that moves carbon between the atmosphere, oceans, biosphere, and lithosphere. When volcanoes spew carbon dioxide into the air, it can be absorbed by the oceans and used by marine organisms to build shells, which eventually sink to the seafloor and become limestone. Plate tectonics pushes that limestone into the mantle, storing the carbon for millions of years before it might be released again by volcanism. This cycle regulates the temperature of the planet. Too much carbon dioxide, and the greenhouse effect runs away, like on Venus. Too little, and the planet freezes. Earth has managed to maintain a balance, keeping enough carbon in the atmosphere as a greenhouse gas to maintain liquid water, but not so much that it boils the oceans. This regulatory system is what allowed life to emerge and flourish. It required the right conditions, a tectonic system to recycle the carbon, liquid water to dissolve it, and a biosphere to actively participate in the cycle. 55 Cancri E has none of these. Its carbon is permanently locked away, unable to participate in any atmosphere or climate regulation. It has no water, no plate tectonics, and certainly no life to cycle the carbon. It represents one extreme end of planetary evolution, a carbon-saturated world. Earth represents the other, more delicate extreme, a world that has managed to hide most of its carbon away, leaving just the right amount in circulation to sustain a temperate climate and a vibrant biosphere. The carbon paradox therefore forces us to reconsider the requirements for habitability. It is not enough for a planet to simply have the right elements. It must also have the right planetary systems to manage those elements. A world with too much surface carbon becomes a diamond, a graphite, or a tar pit, sterile and inert. A world with too little carbon might not have a strong enough greenhouse effect to maintain liquid water. Earth found the golden mean. The existence of 55 Cancri shows us that our planet's carbon cycle is not a given. It is a rare and precious piece of planetary engineering. It also expands our view of what to look for in other stars. A star with a very high carbon-to-oxygen ratio might be a warning sign that any terrestrial planets it hosts could be carbon worlds, likely lacking the water and dynamic systems needed for life as we know it. The study of this diamond planet thus transforms our understanding of our own world. We begin to see Earth not just as a ball of rock, but as a complex, self-regulating system where geology, hydrology, and biology are intricately linked through the element of carbon. The carbon that is so rare in our rocks is the same carbon that makes up our bodies, connecting us directly to the cosmic cycles of starbirth and death. 55 Cancri A, in all its brilliant, dead glory, is a reminder of how that same cosmic abundance could have turned out so differently. It is a world where carbon won, dominating the geology completely and smothering any potential for the chemistry of life. Our world is one where carbon was tamed, regulated, and put to work in the service of complexity. This is the ultimate lesson of the carbon paradox, that life depends not just on the presence of key ingredients, but on the existence of a delicate and active planetary recipe that can balance those ingredients against the relentless forces of physics and chemistry. The universe is full of carbon, but only in very special places does that carbon get the chance to become something more than a crystal. Contemplating the profound lessons of the carbon paradox naturally leads to a wild, science fiction-inspired question. What would it actually take to go there? To launch a mission, whether for exploration or for the fabled mining operation, to 55 Cancri A, while a thrilling thought experiment, it immediately crashes against the unforgiving wall of physical reality, exposing challenges so monumental that they render the endeavour impossible with any technology we can conceive of now or in the foreseeable future. The first and most obvious barrier is distance. The planet is 40 light-years away. This is not a mere hop. It is a chasm so vast that it defies human intuition. Light itself, the fastest thing in the universe, takes 40 years to make the journey. Our fastest spacecraft to date, the Voyager probes, are travelling at a tiny fraction of light speed, at their velocity. A trip to 55 Cancri A would take over 500,000 years. Simply put, with conventional chemical rockets, the journey is a non-starter. The spacecraft would be obsolete dust long before it arrived. So, we must imagine a future with advanced propulsion, perhaps nuclear fusion or something even more exotic like antimatter engines. Let us be wildly optimistic and postulate a vessel that can achieve 10% of the speed of light. Even at this incredible velocity, the one-way trip would still take 400 years. This immediately introduces the problem of time. A 400-year journey is a multi-generational venture. The crew that arrives would be the distant descendants of the crew that left. They would need a self-sustaining closed ecosystem, a veritable ark, capable of supporting human life for centuries without any resupply, surviving the perils of cosmic radiation, microgravity, and psychological isolation on a scale we can barely imagine. The energy requirement for such a journey is another insurmountable hurdle. Accelerating a spacecraft of any meaningful size to 10% of light speed requires an amount of energy that dwarfs our entire global civilization's current annual output. It would necessitate power sources we have not yet invented, perhaps harnessing the mass energy of entire asteroids. The sheer cost in resources would be astronomical, demanding a unified global effort unlike anything in history, all for a mission with no guaranteed return. Then comes the challenge of communication. With a 40 light-year distance, a simple round-trip message takes 80 years. There is no real-time control from Earth. The mission would have to be entirely autonomous. capable of navigating interstellar space, performing orbital insertion, and conducting all operations without any input from home for decades at a time. The spacecraft's computers and systems would need to remain functional and error-free for centuries. Now, assume this miracle ship actually arrives after 400 years. It then faces the problem of the destination itself. 55 Cancri A is a hellscape, orbiting 25 times closer to its star than Mercury. The radiation environment is lethal. The planet has no magnetic field for protection, and its surface temperature is hot enough to melt iron. Any probe or lander would need shielding far beyond anything we have ever built just to survive for more than a few seconds. The surface gravity is more than twice that of Earth, making any landing maneuver and subsequent operations incredibly energy intensive. The surface itself might be a global ocean of lava, or a solid crust of diamond and graphite. Mining in such an environment is a fantasy of engineering. How do you anchor a drilling rig on a surface that might be molten? How do you operate machinery in thousands of degrees of heat, under crushing gravity? With no atmosphere for cooling, the tools would need to be made of materials that do not yet exist. The act of extracting a diamond, one of the hardest substances known, from a planetary crust, is a feat in itself. Now, let us say you miraculously succeed in mining a ton of diamond. You now face the return journey. This requires the spacecraft to have enough fuel left after 400 years of travel to launch from a high-gravity world and accelerate back to 10% of light speed for another 400-year trip home. The mass of the fuel required for this round trip makes the initial energy problem even more absurd. Finally, after a total of 800 years, the ship returns. What is the payoff? As discussed earlier, it is economic nonsense. Bringing back a vast quantity of diamond would instantly destroy its market value. The scarcity that creates its worth on Earth would be obliterated. The entire venture would be the most expensive, multi-generational project in history, only to return with a cargo that is now worthless. The resources expended, the energy, the materials, the human effort, would be astronomically greater than any potential financial gain. The true value of 55 Cancri E lies in the knowledge we gain from observing it from afar, not in its material resources. This thought experiment serves a vital purpose. It clearly defines the boundary between exciting science and practical impossibility. It teaches us humility, showing us that the universe is not a resource to be plundered, but a wonder to be understood. The challenges of interstellar travel to a world like this highlight the incredible fragility and rarity of our own planet. The energy and intellect required for such a futile mining mission would be far better spent on solving problems here on Earth, on exploring our own solar system, and on building telescopes that can bring the cosmos to us. The dream of visiting a diamond planet is a captivating story, but it is a story that belongs firmly in the realm of fiction, a reminder that some treasures are meant to be admired from a distance, not possessed, while the physical journey to 55 Cancri A remains a fantasy. Its discovery triggered a different kind of voyage entirely, one that travels at the speed of thought and imagination through the realms of science fiction and popular culture. The moment this world was hypothesized to be a carbon planet, with its interior potentially laced with diamond, it leapt from scientific journals into the collective consciousness, becoming a modern icon and a powerful source of creative inspiration. It provided something rare, a scientifically plausible foundation for a concept that had previously been pure fantasy. For decades, science fiction authors had dreamed of worlds made of precious materials, asteroids of gold, mountains of gemstones, but these were usually narrative devices, metaphors for greed and ambition, with little basis in actual astronomy. 55 Cancri changed that. Suddenly, here was a real planet, orbiting a real star, that scientists were seriously suggesting could be composed largely of diamond. This validation from the scientific community gave storytellers a new, powerful tool. It allowed them to ground their most extravagant tales in a kernel of truth, making the impossible seem suddenly, thrillingly possible. The planet instantly evoked classic narratives about the perils of untamable wealth and the human tendency to covet the unattainable. It brought to mind stories like the myth of King Midas, where the gift of turning everything to gold becomes a curse, or the classic science fiction trope of the resource-rich, deadly world that lures explorers to their doom. The very idea of a diamond planet taps into deep-seated themes of ambition, the folly of valuing material wealth over all else, and the inherent dangers of the unknown. In this sense, 55 Cancri became a contemporary stand-in for the legendary El Dorado or the cursed treasure of a dozen pirate tales, but transposed onto a cosmic scale. It serves as a perfect setting for stories about corporate overreach, where future megacorps launch doomed expeditions to mine its riches, only to be defeated by the sheer, violent physics of the environment. It fits narratives about the ethical dilemmas of exploitation, even on an uninhabited world, and the question of whether some things in the universe should remain untouched by human hands, beyond just wealth. The planet's extreme conditions, the tidal locking, the lava oceans, the diamond crust, fire the imagination of writers and artists. What kind of life, if any, could evolve in such a place? Could there be crystalline life forms, silicon-based or even carbon-based entities that live within the diamond mantle itself? While scientifically highly unlikely, it is a fantastic concept for stories exploring the very definition of life. The permanent day and night sides create a natural dramatic backdrop for tales of two divergent societies on a single world, or for a desperate struggle for survival in the narrow twilight zone. The planet has appeared directly in various media, from being named in episodes of popular television series to serving as the explicit inspiration for alien worlds in video games and novels. Its name alone conjures an immediate image. More broadly, it has enriched the entire genre of hard science fiction, giving authors a real-world template for constructing believable exotic planets. It has also influenced public perception and education. The catchy Diamond Planet nickname is a gateway drug to science. It draws people in with the allure of treasure, but then reveals the far more fascinating reality of planetary science, stellar chemistry, and orbital dynamics. It makes complex astrophysical concepts accessible and exciting. A headline about a diamond world is more likely to capture someone's attention than one about a high-density, carbon-rich super-Earth. And that initial hook can lead to a deeper appreciation of the science behind the sensation. In this way, 55 Cancri performs a vital public service, acting as an ambassador for exoplanetology. It demonstrates that the universe is not just a collection of points of light, but a repository of endless wonders, some of which are stranger and more brilliant than anything we could have invented. It has become a symbol of the modern age of discovery, a reminder that our telescopes are not just finding new planets, but are uncovering new kinds of worlds that challenge our very definitions and expand our sense of what is possible. It fuels the curiosity of a new generation, inspiring them to look up at the stars and wonder what other marvels are waiting to be found. The planet's legacy in culture is therefore twofold. On one hand, it serves as a cautionary symbol, a cosmic memento mori about the futility of material desire in the face of an immense and indifferent universe. On the other, it is a beacon of inspiration, a testament to human curiosity and our drive to explore and understand. It shows that science and imagination are not opposed, but are partners in the great human endeavour to comprehend our place in the cosmos. The true value of 55 Cancri A, in a cultural sense, is not the diamond it might contain, but the stories it spawns, the questions it raises, and the sense of wonder it ignites. It proves that a world can be uninhabitable and yet profoundly alive in our minds. A fixture of our cultural landscape as surely as it is a physical body orbiting a distant sun. It has secured its place not just in the catalogue of exoplanets, but in the library of human myths and dreams. A shining example of how a scientific discovery can resonate far beyond the laboratory and into the very heart of our creative spirit. The discovery of a world like 55 Cancri a planet potentially forged from diamond, inevitably sparks a cascade of even more fantastical questions. If a planet of diamond is possible, could there be other worlds just as exotic, perhaps composed of different precious stones? Could the universe harbour planets of sapphire, ruby, or emerald? While it sounds like the premise of an elaborate fantasy novel, the question is actually a serious one in exoplanet science, and the answer lies not in geology, but in the fundamental chemistry of stellar systems. The possibility hinges on the specific elemental ingredients available in a protoplanetary disk and the chemical conditions under which planets form. Let's start with diamond itself, as it's the simplest case. Diamond is not a mineral in the complex sense. It is an allotrope, a specific crystalline form of a single element, carbon. For a diamond world to form, you need a system with an overabundance of carbon relative to oxygen. In such an environment, carbon atoms can bond together in vast quantities, and under the immense pressures inside a large planet, they arrange into the diamond structure. This is what we believe happened with 55 Cancri E. Now, consider other gems. A sapphire or a ruby is not a single element. They are both varieties of the mineral corundum, which is crystallized aluminum oxide. For a planet to have a significant portion of its mass made of corundum, it would require a very specific and likely rare stellar environment. The star would need to have an extremely high abundance of aluminum relative to silicon in our solar system and in most observed stars. Silicon is much more abundant than aluminum. Silicate minerals, which contain silicon and oxygen, dominate rocky planet formation. For a sapphire planet to be conceivable, you would need a system where this ratio is inverted, where aluminum is a primary building block instead of silicon. In such a disk, aluminum could condense and form minerals like corundum in large quantities. If a planet then accreted from this aluminum-rich material, and if conditions in its interior were right, you could theoretically form extensive layers of corundum. The colour, whether it becomes a blue sapphire or a red ruby, would depend on trace impurities like titanium or chromium, which would be present in minute amounts. So, while vastly less probable than a carbon planet, a world with a crust rich in sapphire or ruby is not completely outside the realm of chemical possibility. It would just require a very peculiar stellar composition that favours aluminum over silicon. Next, consider an emerald. An emerald is even more chemically complex. It is a variety of the mineral beryl, which is a beryllium aluminum cyclosilicate. Its chemical formula is a mouthful, requiring beryllium, aluminum, silicon, and oxygen in very specific proportions. Beryllium is a relatively rare element in the universe. For a planet to form with emerald as a major component, you would need a stellar system that is not only rich in aluminum and silicon, but also exceptionally enriched in beryllium. The chances of all these elements coming together in the right ratios to form planetary-scale deposits of beryl are astronomically low. You might get small veins or inclusions, but an entire emerald planet seems incredibly unlikely. The same logic applies to other precious stones. Topaz, dotted ore, for instance, is a silicate mineral of aluminum and fluorine, requiring a fluorine-rich environment. Amethyst is a variety of quartz, which is silicon dioxide, a very common mineral, but for it to form a planet, you would need a world almost entirely of silica, which is also possible but would have its own unique formation path. The broader point here is that 55 Cancri E has conceptually opened a door. It has shown us that our solar system's recipe for planets, iron cores, silicate mantles, is not the only one. By changing the underlying chemistry of the protoplanetary disk, you can get entirely different classes of planets. Carbon planets are the most likely alternative because carbon is a cosmically abundant element. Other gemstone planets are much more far-fetched because they require rarer elements or more complex chemical combinations. The study of stellar atmospheres gives us a way to search for these exotic worlds. By analysing the spectrum of a star, astronomers can determine its chemical composition, including the ratios of carbon to oxygen, aluminum to silicon, and other key elements. A star with a very high aluminum to silicon ratio would immediately become a prime target in the search for a sapphire world. We are not there yet in terms of detection capabilities, but the theoretical framework is now in place. It is also important to remember that these would not be glittering, faceted worlds as we imagine them in a jewellery store. A sapphire planet would not be a single, giant, blue gem floating in space. It would be a rocky world where the dominant mineral in its crust or mantle is corundum. The surface might be rough, fractured, and mixed with other minerals, looking more like a vast, blue-tinged geological formation than a polished stone. The conditions on these worlds would likely be as extreme as those on 55 Cancri A, if not more so, depending on their orbit and size. The value, again, would be purely scientific. Finding such a world would be a monumental discovery, telling us that the universe's palette for planet building is even more diverse and surprising than we ever dreamed. It would provide a profound insight into the nucleosynthetic processes in stars that create these elemental imbalances. So, while we should not expect to find a catalogue of gemstone planets anytime soon, the fact that we can even seriously contemplate their existence is a testament to how 55 Cancri A has expanded our horizons. It has taught us to think beyond the silicate paradigm and to consider the full, wondrous variety of chemistry that the cosmos has to offer. The diamond planet was the first step. It showed us that such exotic worlds are possible. The search for others is now a matter of looking for the right stellar signatures and hoping that our telescopes become powerful enough to find these needles in the cosmic haystack. Each one would be a natural laboratory, teaching us not about wealth, but about the fundamental and beautiful laws that can assemble atoms into worlds of breathtaking variety. The contemplation of these potential gemstone worlds, from diamond to sapphire, inevitably leads us from the external cosmos to an internal reflection, forcing us to confront a profound philosophical question. What does the existence of a diamond planet tell us about our own deeply held notions of rarity and value? 55 Cancri E acts as a powerful philosophical mirror, reflecting back at us the arbitrary and anthropocentric nature of our economic and cultural systems. On Earth, a diamond is a symbol of ultimate value, synonymous with luxury, commitment, and status. Its worth is built upon a foundation of controlled scarcity, meticulous marketing, and cultural tradition. We mine it from the depths of the earth at great cost and risk, polish it to brilliance, and assign it a price that far exceeds its functional utility. This value is a human invention, a story we tell ourselves. Now, consider 55 Cancri E. Here is a world where this substance we revere is not rare. It is not a precious gem found in isolated pipes. It is the bedrock. It is the planet itself. The very concept of a diamond there is meaningless in our economic terms. It is simply rock, the commonest material in existence. This stark contrast exposes the fragility of our value systems. It demonstrates that what we consider precious is entirely dependent on context, on our planet's specific geological history and our own social constructs. On a cosmic scale, a diamond is just carbon atoms arranged in a particular lattice structure under pressure, a common outcome in certain planetary conditions. The universe has no inherent concept of value. It simply follows the laws of physics and chemistry. The planet holds up a disorienting mirror to our culture of consumption and materialism. We fight wars and build empires for control over resources we deem precious. Yet here is an entire world made of one of those resources, and its existence renders the resource conceptually worthless. It symbolically annihilates the foundation of desire for such material possessions. If you have a whole planet of diamond, what is a single diamond worth? Nothing. This forces a humbling perspective shift. It asks us to question what truly holds value. The diamond planet's real worth is not in its material composition, but in the knowledge it provides. The scientific data we glean from it about planetary formation, stellar chemistry, and extreme environments is the actual treasure. This knowledge is unique, replicable, and enriching to the human mind. It expands our understanding of the universe. In this sense, the planet teaches us that the most valuable things in the cosmos are not objects, but information, experience, and consciousness itself, life, and the capacity to appreciate and understand the universe is the true rarity. We spend our lives chasing sparkling stones, while the greatest marvel, a living, thinking being capable of looking up and deciphering the light from a world 40 light years away is the most common thing in our daily lives. Yet the rarest phenomenon we have ever encountered in the cosmos. The diamond planet is a lesson in cosmic humility. It shrinks our human dramas of wealth and possession to their proper, insignificant scale. It shows us that we are on a small, rocky world in a vast universe that operates on principles far beyond our petty economies. Our definitions of precious and rare are provincial, limited to the narrow context of our single planet. The existence of 55 Cancri E broadens that context to a galactic scale, and in doing so, it challenges us to redefine our priorities. If we could internalize this perspective, it might lead us to value different things: the health of our own planet, the pursuit of knowledge, the fostering of culture and art, and the well-being of our fellow humans. These are the things that are genuinely rare and precious. A clean ocean, a stable climate, a peaceful society. These are achievements far more brilliant and difficult to obtain than any gemstone. The diamond planet, therefore, is more than a scientific curiosity. It is a philosophical tool. It helps us see our own world with new eyes. The Earth is not valuable for the diamonds that might be hidden in its mantle, but for the thin, vibrant film of life that covers its surface, for the complex systems that maintain its habitability, and for the intelligent life that has evolved to contemplate its own existence. The carbon on Earth is valuable not as crystal, but as the backbone of every living thing. This is the profound irony and the ultimate lesson. 55 Cancri E, a world of dead, crystalline carbon, dot, shows us that the living, Cycling carbon of Earth is infinitely more marvellous. It teaches us that value is not an intrinsic property of matter, but is assigned by life and consciousness. The universe is full of atoms, but only in very special places do those atoms come together to form something that can assign value, that can wonder, that can love, and that can look at a distant diamond hell and understand its place in the grand scheme of things. That capacity for understanding is the real rarity. That is the treasure we should be cherishing and protecting above all else. The diamond planet's greatest gift is not what it is, but what it reveals about us. It holds up a mirror and shows us our own folly, our own potential, and the breathtaking fragility and beauty of our own living world. It asks us to reconsider what we worship, what we strive for, and what we leave behind. In the silent, blazing light of that distant sun, our precious stones lose their luster, and the true gems, knowledge, life, and wonder, shine all the more brightly. The profound philosophical questions raised by 55 Cancri A bring us to the final and perhaps most important aspect of this world, its enduring legacy. What is the ultimate impact of this discovery on the field of science? The legacy of 55 Cancri E is profound, transformative, and far-reaching, cementing its place as a landmark in the history of astronomy. It was one of the very first rocky exoplanets to be detected and then characterized in significant detail, acting as a trailblazer for the entire field of exoplanetology. Before its discovery, our understanding of terrestrial planets was almost entirely based on the four worlds of our inner solar system: Mercury, Venus, Earth, and Mars. We naturally assumed that rocky planets elsewhere would be rough analogues of these, variations on a theme of silicate rocks and iron cores. 55 Cancri E shattered that assumption. It was the world that proved the universe was not just making more of the same. It introduced a whole new class of planetary objects, carbon super-Earths. This was a paradigm shift of the highest order. It forced astrophysicists and planetary scientists to throw out their old playbooks and develop entirely new models of planetary formation, interior structure, and atmospheric evolution. The planet's bizarre density was the key that unlocked this new way of thinking. It could not be explained by traditional models, demanding the inclusion of new materials and new chemistry. Scientists had to create sophisticated computer simulations to understand how a world with a diamond mantle would behave, how it would cool, and what its surface would be like. This pushed the boundaries of computational astrophysics and geophysics. The planet also became a crucial testbed for observation techniques. Its short orbital period and proximity to Earth made it an ideal laboratory for developing and refining the methods we now use to study other exoplanets. The combined use of radial velocity and transit data to determine density became a standard protocol, largely pioneered on worlds like this. The attempts to study its atmosphere with Hubble and Spitzer, even the null results, taught us invaluable lessons about the challenges and limitations of remote sensing, lessons that directly inform the observation strategies for the James Webb Space Telescope. Furthermore, the study of 55 Cancri E highlighted the critical importance of stellar chemistry. It showed unequivocally that the composition of a star is the primary blueprint for its planets. A star with a high carbon-to-oxygen ratio will likely produce carbon-rich planets, a fundamental insight that now guides where we point our telescopes in the search for Earth-like worlds. We now know to be cautious of stars with the wrong chemical recipe if we are looking for a true Earth analogue. The planet's extreme nature also helped define the outer boundaries of habitability by being so utterly and definitively hostile. It helped scientists more precisely define the conditions necessary for life. reinforcing the concept of the habitable zone as not just a region of temperate temperature, but one where a planet can maintain a stable atmosphere and liquid water. Its legacy is thus also one of contrast, making us appreciate the delicate balance of our own planet all the more. Beyond the strict confines of science, its legacy is one of inspiration. It captured the public imagination like few other exoplanets, becoming a symbol of the strange and wonderful discoveries awaiting us in the cosmos. It demonstrated that the universe is capable of creating worlds more imaginative than our wildest science fiction. It inspired a new generation of scientists, engineers, and dreamers to look to the stars. The story of 55 Cancri A is a testament to human curiosity and ingenuity, from detecting the tiny wobble of a star 40 light-years away, to measuring the minute dip in its light, to deducing the presence of a diamond mantle deep within its interior. The entire saga is a brilliant example of the scientific method at work. It is a story of hypothesis, observation, revision, and breakthrough. The planet's legacy is not static. It continues to evolve. Right now, it is a prime target for the James Webb Space Telescope, and the data we gather in the coming years will write new chapters in its story, refining our models and likely surprising us once again. It stands as an enduring icon, a reminder that the universe is vast, diverse, and constantly challenging our assumptions. It redefined what a planet could be, and in doing so, it forever expanded our cosmic perspective.